Test 1, 2, 3. Test 1, 2, 3. Test 1, 2, 3. Yeah, it's ready.
Great. So a very warm welcome to everybody. I'm standing here in place of Jakob Ostergaard, who unfortunately had to excuse himself because of severe back pain. Since last night, he's not able to move very well. So we are very delighted to have you here. It's one of our first events after COVID, and we hope to have many more of those in the near future. We have prepared an exciting program, we think. And without further ado, I would like to introduce Fitim Krezi, the chairman of the steering committee of multiDC, to offer his welcome.
Yes, can you hear me? Dear all, welcome. I'm very delighted and happy to see all of you attending here physically, and also to you guys that are online. My name is Fitim Krezi. I work at Energinet, mainly involved in the energy islands, been doing that for some years now. And I'm also the chairman of this multiDC event. And on behalf of the multiDC event, I would like to once again welcome all of you and send a special thanks to all who has contributed through the last 4 years of this project. And most thank you to the PhD student who has done the hard work here. So we are grateful for it. When this multiDC event or multiDC project started back in 2017, the island wasn't that very known. Yes, we worked with it at Energinet, but this project has also helped us in evolving and also developing those islands in many ways. And I have been glad and happy to be part of both things. And a special thanks to you guys and also to the different partners here, the university, KTH, DTU, and also Liège University for your hard work and hard contribution here. A special thanks will also go to our TSO partner, Svensk Kraftnet, but not last but not least, ABB for, or now called Hitachi Energy, for your contribution and your share of real life work to this project. So without not taking that much time, I would like to welcome all of you and hope that we'll get a really good day out of this. And please do not hesitate to ask any questions that you may have during the day, or otherwise I will be here around after the event, that if some of you have some question to the project, but also to the energy islands in general, please ask. So I will leave the floor to the first, and maybe if Spiros can take it.
Yeah, so thank you very much, Fitim. So the first speaker, I have the pleasure to have with us Carsten Chacha. He's a chief consultant from Dansk Energy, Danish Energy, and he's going to talk to us about if the energy islands will become what the iPhone has become to the smartphone. I would also like to say at this point that all the participants online, and I know that we have several of them, please, you're very welcome to ask any questions. This is a hybrid event, and the majority of the people are actually connected online. Carsten.
Sure. Yes, thank you very much for the invitation. It's good to be back here at DTU. I studied here a while ago, but sadly I haven't been back much since. But it's good to be here today. My name is Carsten Tjertje. I'm with the Danish Energy. We are, for those of you who don't know us, we are the lobby organization for the Danish energy companies, and we represent the interests of both generators and retailers, traders, and distribution grid. I've chosen a somewhat popular scientific header for this brief presentation here today. So, will energy islands be to offshore wind deployment what the iPhone was to smartphones? And maybe it's a bit of a bold move here, because I know that Apple products are not necessarily best in class among engineers. So maybe I'm taking a bit of a risk here, but let's see if I can get away with it. I don't know if you've seen the official launch of the iPhone back in 2007. Basically just Steve Jobs on a podium with a very few messages. And what he did was to sort of build up an anticipation. So he came out, he says, I have 3 things for you today. 3 new things. It's an iPod, it's a phone, and it's an internet device. And then he sort of looks at the crowd and waits a bit to see the reaction, and he repeats himself. So it's an iPhone. Oh, it's an iPod. It's a phone. It's an internet device. And then after a while, he says, "Do you get it? It's not 3 items. It's not 3 devices. It's 1 device." For me, that has a similar sort of reference as the energy islands. So we have an island, we have offshore wind, and we have transmission infrastructure. And it's not 3 projects, it's 1 project. And for me, that's quite interesting. And besides this first comparison, if you watch this launch by Steve Jobs, it's on YouTube. It's quite interesting if you haven't seen it. Then he goes on to look at, okay, so why are we doing the iPhone? So he says, okay, we have sort of the conventional so-called smartphone segments. So he pulls out a picture of what was existing at the time. And then he says, okay, so these are so-called smartphones, but I don't think they're really smart because they have this plastic keyboard. It's fixed, it's there all the time. You can't add any additionalities to it. You can't further develop it. It's really fixed and stationary. So he said, that's why we're going for the iPhone. So it has a touch screen. The keyboard goes away when you don't need it. You can add a lot of new functionalities to it. So he says that's the future. And for me, you could somehow make a link to that into the way we build offshore wind today in Denmark. So we've built offshore wind for a while. We've done it radially. We do it 1 park at a time. We connect it directly to the homeland, so to say. And then at some point when we have a lot, we build an interconnector to be able to balance it with neighboring countries. Now, a new approach is the energy islands. So here we do a more top-down approach. Okay, so we plan everything from the start. And when we're talking about the North Sea energy island, there is a physical island, there is offshore wind planned, and there is interconnection and transmission infrastructure planned. So in that sense, we could be talking about a sort of a change in approach, just like Apple did with the smartphone. Now, in order for this new approach to make sense, we have to have some conditions to be met. One condition would be that I guess it has to be more cost efficient with the new approach than the old approach. Otherwise, it doesn't really make sense, I guess. And another condition we need to meet is that we need to be pretty sure that we're going to build the amount of offshore wind we set out up front, because if we set out to build 10 and we only build 3, then it's going to be very expensive, and then we haven't achieved anything. So that's another condition we sort of need to address. And these two conditions, I'll just touch a bit upon both of them. So in order to say how much offshore wind do we need, I guess a starting point would be the demand. So what is the electricity demand going forward in Denmark? Well, there are various sources to that. Last year, the Climate Partnership for Energy and Utilities published a report, a roadmap, and in that there is the industry view on what will the development be in the demand. So we have today with about 35 terawatt hours, and there is an estimate of a doubling towards 70 terawatt hours. And the individual elements in that is that we have a big chunk from power to X, so taking renewable electricity, feeding it through electrolyzers and making hydrogen and further developing synthetic fuels. A large chunk from data centers, and then electrical heating through heat pumps, both district and residential and industry. Then we have transportation, both road and rail, and then a couple of other elements. So giving us a total towards the 70 terawatt hours we see here. So essentially a doubling the power demand from now till 2030. But when we're talking about the energy islands, we have to look beyond 2030, because not very much will be up and running by 2030 actually. So it's actually the period ahead of 2030. And there, if we want to sort of have a demand projection, we need to bring out an even larger crystal ball than this was. So we have attempted that at Danish Energy. We do yearly or once in a while, we do a sort of an electricity price forecast. And here we look towards 2040. So you see here still, we start at the 35. We have the doubling towards 2030, around 70. And then in our prognosis, or our estimate, it's not really a prognosis because we're 20 years ahead. So it's really an estimate, I have to underline. We are moving well beyond 100 terawatt hours. And for some, that might be sort of a high number and maybe a bold number for Denmark, but we do see a continued line towards the 2050 European climate neutral targets, in which we will need a lot more PTX to abate in the hard to abate sectors, and we will also need more direct electrification. So the additional from 30 to 40 is maybe 1/3 direct electrification and 2/3 power to X. And one of the reasons why we might need a lot of power to X is when we look at Denmark alone, for some people it might be overwhelming to think of an island with 10 gigawatt offshore wind, and what are we going to do with all this wind power? But if we take a more regional approach, the Danish contribution to just the surrounding countries is today rather small, and there's no reason why that shouldn't grow given the resource and the offshore wind potential we do have. And there is a big potential to abate the fossil fuels and even some of the nuclear in our neighboring countries. So we do see quite a large potential. So how do we meet this demand of well beyond 100 terawatt hours? So I put the estimated demand out here, and then sort of trying to break down the stack of generation that can meet the demand. So if we look at what we will have left of the renewables that are there today, so maybe around 6 terawatt hours, so not a lot. Then the next contribution is from the most recent offshore wind farm, Kriegers Flak, that came online a short time ago. And then we're waiting the two nearshore coast farms called Vesterhav Syd and Nord, which have been delayed a bit. Then there's the the two new large offshore wind farms from the new energy agreement, Thor and Hesselø. Then we move into the energy island with the first stage. So with the 3 gigawatts in the North Sea and the 2 gigawatts on Bornholm, that adds quite a big contribution. Then I've sort of created the picture that now we're moving into to a new era where everything is energy islands. Everything is not going to be energy islands. So we're still going to see some of the traditional approach. So we'll still have a lot of onshore wind. We'll have a lot of onshore PV, and there will still be some nearshore, offshore wind that would be developed perhaps closer to the coastal area and then directly integrated to mainland. And then we have the second stage of the energy islands, the 7 gigawatt projected for the North Sea energy island. So all of this, if you add this up, it doesn't really meet the world beyond 100 terawatt hours that I've sort of put as the estimate. But here we do have to keep in mind that there's still an expectation that we will have thermal capacity in 2040. So the Energy Agency has estimated about 3 gigawatts of capacity. We don't really know how many terawatt hours that will translate into, but there will be some. So maybe this gap will be met, maybe not. But just to say, so even with the full scope planned energy islands, we're just barely making the demand that we have put forward as an estimate. So a message here is to those who think that building so much offshore wind in Denmark is overwhelming. We're actually going to need it. So it's actually well planned for. And an additional uncertainty in this is that we're seeing that some of these renewable projects are facing difficulties. So the Hesselø project is being discussed right now because the Sea Basin Foundation is not great compared to other sites. So there's a discussion right now whether it can be possible to continue or we need to relocate the site. We've seen some delays in the Vesterhav Syd and Vesterhav Nord projects. And just yesterday, it was announced that some of the onshore tenders for wind and solar PV were left void, so nobody used them because the model was a bit too strict. So there are uncertainties whether we will actually be able to meet all these renewable projects. Another part of what has been maybe overwhelming for some regarding the energy islands is just the cost estimate, the overall cost estimate. So very quickly, it was out that, okay, so we're talking about 210 billion Danish kroner. So this is massive. This is all taxpayer money. Why are we doing this? But when you try to break down the numbers, you'll see that 95% of the costs are actually the building blocks that we have used in the radial build out. So half of the cost are the turbines and foundation, and then almost the other half is transmission infrastructure. Then we have the island, which will be about 10 billion Danish kroner. And when we look into who will own the different parts, so the wind turbines and foundations, private investments, the grid, the array cables will probably fall under the private investments, but the rest will be TSO owned, we expect. Then you have the island, and the island will be split 50-50 between the state and a private investor. So there's a lot of private capital in here. It's not $210 billion of taxpayer money. So the condition on the volume is met according to our estimate. We're going to need all the production from the offshore wind. Now the condition on economies of scale. So is it more cost efficient to build with the new approach, a top-down approach with the energy islands and the planning from the start, than it is to sort of step by step incrementally doing the radial approach? Well, there's not much data on this, but there is the report from COVI to the Energy Agency, and when you try to compare the cost of those with the same export systems, so with roughly the same amount of interconnection, because whether you build 10 gigawatt like this or 10 gigawatt like this, to some extent, and then of course, depending on demand and flexibility, to some extent, you will probably need roughly the same export system to neighboring countries. So when we look at it, we get a cost estimate that it will be 5 to 10% more expensive to go the radial way. So for us, this condition of economies of scale is also met. So in our view, we have both the condition on that the power will be needed, perhaps we'll maybe even need more, and the condition of economies of scale. So for us, it's a good idea to go ahead with this new approach and doing the energy islands as a top-down approach. Now, so far, I've only been talking about the hardware, so wind turbines, the cables out there. But if you have watched the iPhone launch back in 2007, then in the second half, Steve Jobs really comes into the software, and he says, okay, the software might be even more important than just the hardware. And when you're talking software, you're talking an operating system. And for the energy island, I would say there are two operating systems. So there's a market operation, and then there's a system operation. And if we start with the market operation first, so if one thought that the hardware and the construction is complicated, then the market operations become more complicated. Because here we have to find out, so how do we do this? So we have a large island, a lot of generation, perhaps some demand, maybe no demand. It depends on whether it's feasible to have demand out there. But if there's no demand and a lot of generation, then how do you have a price formation on that? So when you connect it to the European wholesale market with day-ahead and intraday markets and bidding areas, how does that work? That's an interesting topic, and the Commission is looking into it at the moment. There are different ways, and both ways sort of creates difficulties with the European regulation. So one way would be to have some of the offshore wind just drawn into an existing zonal market setup and sort of a home market solution, so you get the price that is in the home market. But then there's a new rule that you have to sort of give the interconnection freely, because it's not only a feeder line for offshore wind, it's also an interconnector between Denmark and some of the other zonal market areas down here. So there's a clash there. So another option is to do an offshore bidding zone. So you have an entire sort of semi-isolated bidding zone out there, of course, connected to the coastal bidding zones. But then how do you have a price formation that makes sense out there? You have a lot of generation, little or no demand. So you'll be dependent on the price formation capabilities coming through the interconnectors. And then you're sort of in the unfortunate situation that you will always get the structurally lowest price of anyone you're connected to. So in that way, you're taking revenue out of the offshore wind owners. So how to solve this? You may need to do it the offshore bidding zone way. You may need to redistribute some of the congestion rents that arises. This sort of gets into some of the complexity that is in the market operation, but it's doable. So that part of the operating system, it will be doable. So then there's the system operation. And if you thought the hardware was complicated and the market operation was more complicated, then the system operation is extremely complicated. And that's why I'm glad you are all here, because this is some of the topics for today as well. And I'm not even going to attempt to say something remotely clever on the system operation. I think I'll just sort of end my presentation by saying that I'm happy that the project is up and running, and I'm really looking forward to seeing some of the conclusions from the study. So I think those were my brief words. Thank you.
That's great. Thank you very much, Carsten, for this nice presentation. Are there any questions to Carsten? Okay. Thank you very much. This actually introduced very nicely what we're going to discuss later today, and we're looking forward to more discussions in the next sessions. Thank you very much.
Great. Thank you.
So now I have the pleasure to actually welcome Dr. Cora Pettino-Wagner. She's from TenneT in Germany, but she's also here on behalf of NSOE, the European Network of Transmission System Operators. Cora is actually now getting ready, and we will soon have her on stage.
Yeah, so good morning, everybody. I'm Cora Pettino-Wagner from TenneT TSO in Germany. But as already introduced, I'm not only here as a representative from TenneT, but also representing our work on the NSOE, work we do, since TenneT is a bilateral TSO active in the Netherlands and also in Germany. We are quite active also on the European level and side, and do a lot of work with other TSOs together in order to solve the ongoing issues and discuss and what is really required, not only from the national perspectives, but also from the European perspective. Because yeah, everybody can do its national plans, but in the end it has to work together. And this is actually my topic for today, which I want to present here, what our findings on this matter on interoperability means. So last year, or the end of last year, we published this kind of work in the form of a position paper on the offshore development. And interoperability seems to be one of the enablers for HVDC multi-terminal development in the offshore and in the offshore plans. So I will start with a quick motivation for this topic, and yeah, will guide you through the key messages for interoperability and, of course, the way forward, what we find out, how we want to tackle these challenges. So first of all, yeah, a lot of you guys know all the plannings for the northern for the North Sea, the offshore goals, which we also need to incorporate, etc. And yeah, from today we build predominantly point-to-point links, and as we heard earlier, it's not the most cost-effective way of integrating this high amount of offshore power to the countries, and that's why we want to establish or go to basically the next development step, which are hybrid projects. So not only this point-to-point, which is on the left side, but hybrid projects and also multi-terminal offshore projects. Offshore, yeah, is here in the focus, but it's not only offshore. It's also, I mean, you cannot stop at the coast thinking your DC system. You have to also transport it somewhere to the countries. So, but this kind of planning in hybrid projects and multi-terminal offshore projects, basically, yeah, thereby you are able to integrate a large amount of power. You have a really high potential of cost reduction, and also improvement of the European grid stability, considering this climate neutrality until 2050. And the problem is the HVDC grids can always can grow in the required pace as necessary if interoperability is not an implementation risk. And this is basically one of the big challenges still to cope with. What does it mean? It means basically very simple for the first time that interoperability of a transmission system, its subsystems and components is defined as the ability to function together, seamlessly allowing the transmission at the required power quality and level of security of supply. This is basically what we agreed on would be the message, what all the assets need to cover basically. Because as soon this does not work, TSO will have a high risk in implementation of potential technologies, and also increases cost efficiency in the long term. And finally, I mean, we always say, make DC as easy as AC. Maybe not if it will not be entirely as easy as AC, but on the other hand, we have to open the market for harmonized solutions to come in the near of, or maybe in the area of plug and play somehow. So what does it mean, interoperability, or what does it cover? It covers from the one side, of course, that the components of different technologies need to work together. So there's technological interoperability. So basically, I don't know, a converter station from the first generation needs to also to work together with the next generation from the same vendor. This is the more easy part. And then, of course, also we have to think about requirements for a grid where all the components from different vendors and maybe even different technologies need to work together seamlessly. And this would we cover also as manufacturer interoperability. Yeah, so the role of the TSOs is currently, of course, we need to apply the holistic engineering for our power systems and have the responsibilities of while planning these to guarantee adequate level of supply, sustainability, of course, and robustness of the system. And we are not allowed to discriminate any system users or market players. And the role of the manufacturers currently, they have a really dedicated and detailed expertise for developing and specifying all the assets required for such a system the TSO wants to build up, and harmonize, standardize the specifications in order to achieve and guarantee this seamlessly interoperability. And of course, cost efficiency. But what we need to improve, because this kind of focus within planning changes a bit, that we need to cooperate more closely between the TSOs and manufacturers, because TSOs now not only are the institutions which just buy a system, we also need to take a leading role as infrastructure owners and on the part how to specify the components. And this is this is a bit more complex as in the past, basically. So that's why we identified the current situation. So it's actually demanded that we detail functional specifications and need to recover the required asset behavior for our systems that doesn't disturb or endanger the stability. However, TSOs are not entirely at the moment capable to do that, to have really detailed functional specifications, because for HVDC multi-vendor, multi-terminal, multi-purpose grid, because there's actually currently an absence of operational experience for just systems and also limited knowledge of the full operation risks these solutions might bring. And then we have the vendors, of course. We cannot develop projects if the TSOs cannot provide the detailed functional specifications. So you see, this ends up currently in a kind of vicious circle. Everybody is waiting for the other party to do the first step. And that's why we say This is something we need to overcome. And we really want to solve it. We need to solve it because otherwise these ambitious plans will not work. So we need to agree somehow on the learning curve that maybe specifications doesn't need to be as detailed as required from the first part. So there should be at some point also an iterative process with a lot of blanks to fill out a later place, but also TSOs need to gather this information about expected acid behavior by themselves by using appropriate simulation models. It's not an valid option anymore to skip the optimization of grids, for example, on a load flow basis, for example, just one example. But that's why we have to improve our simulation models and need to understand really what's coming with this new technologies and how do they fit into the grid and what is actually one of which behavior is required and which is not. Because also from Tenet's side, we have a lot of experience with HVDC point-to-point links and even ending up 3 of them in one substations. And then you cannot expect, or we did not expect maybe at the beginning, but you see also that this kind of interactions between the stations might happen. You need to be aware of this. This is one of the examples, for example, that you at the beginning, you cannot cover the full risks entirely if you don't know your asset behavior. So basically a lot of on the to-do list for the TSOs and regarding simulation models improvement, but also from the vendors, we also asked for the commitment to deliver us and to help us providing us exchangeable models for grid planning issues and operation purposes. Finally, it's also, you can do a lot of planning, but at some point you also have to go for projects. So a really demonstration project is required at some point in the near or in the close future, which should not be a one-man show. So basically you have to guarantee that the solutions for this demonstration project are also and scalable to other projects. And we narrowed this. This was a very high level description, but we narrowed it, of course, a bit down. We had said interoperability is really one of the central enablers for achieving HVDC multi-terminal development. And research projects have already outlined a lot of requirements and technical solutions and innovation steps, which are really required for the operation and also protection of those grids. But still a number of open issues are remaining. And we want to take, of course, over responsibility for leading the studies and participating in relevant initiatives on this topic. And we divided those findings not on the technical issue side and on the legal issue side. I mean, I'm a technical guy, but also that's why I can elaborate on the first 4 bullet points a bit more. But of course, they are not only from the technical side, but also from the implementation side, these legal issues, where you maybe as a technician don't think in the first place what's happening or what's also awaiting us here. So I would start basically with the 4 technical issues and what we need to do here, what we are going to do here, and what the impact if we do nothing, if everything remains as it is. So the first point would be the function and operation requirements. We, as TSOs, need to complement the the network code HVDC, which covers a minimum set of requirements for the HVDC system functionality. But we need to formulate this grid or this function requires for DC grid, which consider all the subsystems and components which are playing a major role here. And we need to include it also, these requirements in kind of connection requirements. And on top, we also need to aim for operational guidelines so that we know system similar to the existing ones. It's necessary to define on how such a grid needs to operate because the operation is one part, but also it gets more complicated if you have also market rules playing into this field. And yeah, if we don't do that, basically, it remains that if the DC grid's functional and operation requirements are not available, this we might not be able to achieve interoperability because the lack of clear requirements result in increase of the implementation costs and reduce scalability. We might stick even to a tailored solution for only one project, but not rolling it out in a big scale to the market. And yeah, and also the absence of interoperable grid infrastructure would finally impede the achievement of the energy policy targets. If we are not going, or what needs to be done in a demonstration or in the target environment. So basically, we think not only from the TSO, but the vendors see it the same way, that actually we need to have a really full-scale demonstration project in order to confirm and prove the technology readiness. Because if you don't prove it, then yeah, maybe also the regulators are reluctant on granting the next steps, whatever. So we think that really a big step needs to be taken here by planning a real full-scale project. And you need, ideally, this should be also based on a multi-vendor application case. So basically, including more than one vendors already having this or showing that interoperability might be achieved between different vendors, and also showing that this work between vendors and maybe also different TSOs can be aligned with between European stakeholders. So there are already a lot of initiatives and plans going on. I mean, of course, we have the TYNDP regularly published, but also initiatives as the H2020 promotion project also maybe guided us how you could basically come up with specific solutions. And also on the national levels, we have all possible of ideas how to do the first hubs, the first multi-terminal projects. And yeah, now it's really a matter of how can we work together here and make a corporate plan, or not a corporate, but a cooperative plan on this. Yeah, if none of this multi-vendor project will be initiated, it cannot be demonstrated that interoperability works. And most likely we will interlink to proprietary systems, which is not the aim in the long term. And this for the TSOs, this means basically that we remain stuck to either R&D-based demonstration in specific initiatives, but also tailored solutions on the large scale. Yeah, as I already basically said, we need to adapt our power system engineering processes and plans. We are basically, as TSOs, the only entities who can take responsibility for the development, construction, operation, and maintenance of such kind of offshore grid. So we need to be here in the role and have in the leading role, and also have a clear vision on the risks associated to this. And yeah, and in this kind of planning standards, I already said this, with the simulation models, for example, we need, of course, but also a backup from the manufacturer side, so that we can align this internal processes and plans with new asset behaviors, which we might not know yet. So, and if this planning within the TSO side doesn't evolve, maybe if new technologies and system performances may not be compatible with each other. So we have a higher risks after commissioning of the projects. Maybe we might draft diverging specifications, which may impair interoperability or efficiency, and in the worst case, also system stability. On the other hand, maybe if we see at the end or by implementation, when something doesn't work, then it's really a high risk of reduced or stranded investment, of course. And also here, this kind of interoperability may not be achievable when we are stuck with singles, or when we are stick with single solutions. There was with also a lot of standardization issues come in hand. So not only processes, models, converter controls, and engineering studies. It's a long list basically. what needs to be standardized. Not everything needs to be standardized at the very beginning. As I said, it needs to be an iterative process, because if these issues need to be solved at the very beginning, all of them, I think we really need already or still a lot of years more to being stuck with plans and everything. So but we need to solve it. This is really important. We have the commitment also from on the N2E side from all the TSOs to do so. Otherwise, we cannot compare our results, for example, in terms of interoperability studies, and have the intercomparability of TSO models and manufacturers, which might not be given. And and this is actually the second last point is the most fear of TSOs. They may take over full responsibility without knowledge of the full operation risks. And this is something in such investments, when we talk in such as investments as we heard earlier this day, we really want to have a clearer picture on this basically. So, and now 2 points again to the non-technical issues. Basically, I will simply, because I think the time is also running out, to refer also on the findings on the both listed H2 2020 projects, which are also covered, have underlined the presence of a number of additional non-technical barriers, such as different national legal and regulatory regimes, and existing contractual relations which do not consider multi-vendor setup with the vendors currently. So, and then of course, issues like ownership, warranties, and everything like this when system or components are ordered. Who's taking over the responsibility in such a grid system when vendor B is adapting to vendors A solutions, and this is really also a big issue to be solved. And we recommended a multi-vendor cooperation framework and to solve basically also these issues in parallel. So the way forward, this is my last slide for today. We identified, as I said, a lot of tasks for the TSOs, for the manufacturers, but also for the policymakers, in order to bring everybody on the same page what needs to be done here in a very short time. And so basically the tasks for TSO, I really already elaborated on this in my presentation. And also the tasks for manufacturers, we shared this with them, what we think is necessary to overcome also the shortcomings in the exchange of expertise while still respecting the IP issues. We understand that, especially in terms of models and exchange data, it's really a sensitive topic, but at some point we need to also here find some interfaces and whatever where we can all agree on, which helps us. And of course, the last point, task for policymakers, we also should be enabled to do creating legal and regulatory basis to do that, because at the moment it's even, I mean, Tenet is active in the Netherlands and Germany, and we see and we see it directly in our daily work that it's not always easy having two regulators within one company. And yeah, and when you scale it to Europe, it's even more complicated. And basically, we need to have national support of the regulation bodies and enabling our planning so that we can, yeah, enable or also fulfill all the plannings which we are currently planning in terms of, yeah, a lot of initiatives. Not only from the development side, but also we have with Energinet, the North Sea Wind Power Hub, and there are multiple of these initiatives how to cover the North Sea grid. And yeah, here I'm at the end of my presentation, and thank you very much for your attention. And if you guys have any questions, feel free to ask them.
Thank you very much, Cora. Are there any questions from the audience? Yeah.
Cora, thank you very much for your very good and informative presentation. You mentioned you highlighted two main issues here, which the first one, the technical issue, and then the legal issue. Seen from the NSOE's point of view, which of those two are most difficult to solve?
I think, yeah, at least from the working bodies where I'm talking, most of us are technicians, so I think the legal issues would be harder to solve. Yes.
Yeah.
So the NSOE has a research development and innovation commission that made
Yes.
a proposal about how to solve this. This two flagships project on ACDC, and if you look on that in that roadmap, then the most difficult part is to solve is actually the technical part. It is both, as you mentioned, the interoperability. It is that the vendors tend to keep secrets in major components for simulation that we need for operation simulations. But it is also that we're lacking tools for planning. So the tools that we have for planning, for long-term and maybe a little bit medium-term planning, they are not good enough right now. So we have different challenges. It is in a planning where we lack the modeling tools. It is in the operational planning where we lack also the tools. We lack the dynamic tools for doing this. We lack good protection schemes for how to do the protection when you have a hybrid AC-DC grid, and also when so much grid DC is actually coming. Because if you look, for instance, at Norway, then we know that the majority of the consumption will actually be export. So if one of these DC lines will then have a failure, that will have a huge impact on the frequency. And how do you deal with situations like that? And I think Denmark has already experienced with these kind of issues that I often have to rely on Norway or the import for Norway to deal with these situations. So, but if you look at these two flagships, it's dominated by technical issues, which I named just a few of it. But of course, there's also regulation issues, but they were not really dominating. What is, however, a pity that the NSOE with Tenet and then a number of TSOs in joining that, we proposed a project for actually this offshore demonstration project, but that was actually rejected by the EU Commission, and that was really pity, else we would have already been able to start like a big demonstrator. Yeah. So it is competition, it is vendor lock-in, it's technical solutions, it's simulations, models, protection schemes. And then, and also how do we maintain all this offshore? Because this is offshore, so that's harsh environment. And what is your maintenance strategy for such an offshore park? There are right now no good solution for that either. So we have a number of issues regarding this. And then the legals are the one, but I think they are the least complicated to solve if you compare to the rest.
Maybe
that is just paperwork.
Maybe it appears so because the technical issues we have in our own hands to solve, and the legal issues not. And especially also this year in Germany, we experienced again the influence on politics again, and basically resulting in that one of our new HVDC corridors, which should be multi-terminal ready, was now drawn from us by regulation. So we had to, the project needs to be reassigned, and such things which is not in our hand. The technical issues we can find solution for this. This is why I was motivated for Godi. Yeah.
Very good.
Mm.
So I know we're running a little bit behind time, and actually this discussion will also continue during the panel session, and I'm very much looking forward to that. I also want to take one question from the audience online, because we have many participants online. So the question is are DC breakers still a challenge, a technical challenge? And also in the panel session, we'll have Peter Lundberg from Hitachi Energy, the former IBB, who can also discuss this. But is there a quick answer, or shall we take it later?
A quick answer, and but I will comment on this. So basically, yeah, we actually work a lot of, or we intended we work a lot of on how to analyze or to see this new technology in terms of DC circuit breaker. So basically, we have made within the North Sea Wind Power Hub Corporation frame a lot of consultation rounds now with vendors, also asking for the current state of the art or the technology, and also the problems still to be solved, and where are actually the problems, in order so that we can evaluate it more detailed. And also we have a lot of help on the from an independent laboratory to evolve this. So there are some challenges, but we think these are not challenges which cannot be solved in the next 3 to 5 years.
Great. Thank you very much, Cora. Thank you. Let's thank once again Cora. Yeah. So now you can hear me? Is this working right here? So now we enter the part where we discuss a bit about this project. I think this fits very nicely with what both Carsten and Cora discussed. And I'm going to give an overview of what we have worked on over the past years here in the multiDC project. And then there's a number of presentation demonstrations, live demonstrations that are going to go more in detail. My name is Spiros Hadjivasiliadis. I'm actually the leader of this project and associate professor here at DTU. So there are actually 3 main drivers that have motivated us in working on this concept. So the first is that, as both actually Carsten and Cora discussed, so we're moving into a system, into an energy system with much more renewables. We're moving towards 100% renewables, with many of them actually being converter connected. So we are looking about a system with a low inertia towards maybe even zero inertia AC grids. At the same time, as you have seen, there's a lot of interest and a lot of, let's say, movement towards HVDC lines and HVDC grids. Besides that, we are also in a kind of unique position because Denmark is unique in being involved in 3 first-of-their-kind projects. The first is the Kriegers Flak interconnection, and this has been part of this project from the beginning. This is the first interconnection in the world that integrates offshore wind. And right at the beginning of this project was just announced that Energinet was thinking to build these offshore energy islands, and actually recently the Danish parliament has decided to go forward with the construction. So we're talking about the first hub and spoke configuration in order to integrate the offshore wind. And the decision, at least from the Danish side, is to build 2 such islands. The first is, for the first time, building a first artificial island in the North Sea, and also have a second island in the Baltic Sea around the natural island of Bornholm, where we will integrate offshore wind and then connect that to the neighboring countries. So with this motivation in mind, the multiDC project has been put together. It is funded by the Innovation Fund Denmark, the Grant Solutions Program, and partners to this project are 2 neighboring TSOs, Energinet and Svenska Kraftnät, 3 universities, DTU, who is leading this project, KTH from Sweden, and University of Liège from Belgium, and 1 major manufacturer, that's Hitachi Energy, formerly known as ABB. It's a 3.5 million euro project with a duration of almost 5 years. Will be ending in spring next year. So we have a large and diverse team. Over the past 4 years, there are 20 persons that have been actively involved in this project, based in 3 different countries with 11 different nationalities. You're going to see a number of them today in their presentations. The people actually in the middle row are the ones that have done the hardest work in this project, and we very much thank them for that. So let me now move to the questions that we try to address, and I have divided this presentation in 2 main questions. The first is, what are the possible topologies when we go into this North Sea energy island? And a first topology could be an offshore AC grid, where wind farms are interconnected to the offshore hub through AC, and then have point-to-point HVDC connections to different countries. So in that case, actually, one could think that maybe we don't need 50 Hertz for that, and maybe we could go with low frequency AC, which has which can allow actually longer distances. So we did a thorough analysis about this, and we found out that the benefits from the longer distances, for example, do not outweigh the costs. We are going to need larger transformers, and this also placed offshore. So this solution is not a viable one, and if we go for, we need to go for with 50 Hertz. The second option is to have a multi-terminal DC. And what should happen there is actually that each wind farm shall have an offshore HVDC substation, and then transmit this power to the offshore hub. And from the hub, then this should be distributed to the different countries. What is key, and also Carsten touched upon this, is that we start with 3 gigawatts now, and the idea is that we need to go to 10 gigawatts and even more in the future. So we need something that's modular and something that's expandable. So what we think is that probably there might be a hybrid AC-DC solution, where we are going to have both an AC and possibly a DC ring on the islands. The wind farms will be connected over AC to the AC ring, and then the 2 rings can be interconnected by VAC converters, and then the different countries can be connected either through point-to-point links or through the multi-terminal DC. Both storage can be actually integrated in both rings. It can be in the form of batteries, electrolyzers, and we have heard a lot about. There's a lot of discussion about the power peaks and the production of hydrogen, and also maybe synchronous condensers in order to provide kinetic energy. So the multiDC project has focused on the AC part and the challenges that are entailed within. We think that there has not been investigation of zero inertia or low inertia AC grids at this scale, and we address actually the challenges that are associated with that. We have the connection to 5 VAC converters, and we also investigate the connection of kinetic energy, the integration of kinetic energy storage in the form of a synchronous condenser. So then there are a lot of questions that we have asked related to that. And the first is, we're talking about a zero inertia AC grid. We're talking about very fast transients. How can we handle the transient behavior of such a system in case a fault appears? And in order to address that, we thought, let's maybe connect the synchronous condenser and turn it to a low inertia system. So we investigate both configurations and we try to see what are the benefits and drawbacks with detailed investigations that we'll also show later today. Then there are also other questions. How can we guarantee N-1 security? And how should we coordinate the VSE converters in such a grid? And also, what is the impact of such an island to the operation of the national grids and also to the technical operation and the market operation? So we have designed or defined two topologies, one with a zero inertia and one with low inertia. So actually, Andrea, which we're going to have the next presentation, is going to discuss this more in detail. So the questions that we tried to address is how should the converters share the control effort in order to keep the limits on the island? What is the impact of the offshore disturbances on national grids? And how can the energy islands affect the operation of the national markets? And the presentation right after this from Andrea Tosato will cover all these questions. Besides that, we have also two live demonstrations. The first one is by Brynjar Sevarsson in the afternoon that is going to focus on the low inertia North Sea Energy Island. And we are going to have a hardware in the loop configuration where we try to answer questions related to how can achieve the stability or how can ensure the stability of such a configuration and what are the critical parameters if we want to expand this island with more wind farms, for example, or other interconnected islands. So what are the critical parameters that affect its stability? We also have a second demo by Georgios Misiris, who is going to focus on the zero inertia configuration of such an island and is going to address issues and questions related to how can ensure a stable operation of that and how the current limitation of the HVDC converters affect this operation. So multiDC is not only the North Sea Energy Island, though. So we have done quite some work on how to optimally coordinate or how to best coordinate the HVDC interconnections in order to support the frequency in the Nordic system and how can take advantage of these capabilities. So as you probably know, the Northern European region is one of the most HVDC-rich regions in the world. The first commercial HVDC line was actually built in the Nordics in 1954, and since then many more followed. HVDCs actually offer a lot of capabilities, and not a lot of them are being exploited by the system operation. So what we try to do is to see how can unlock this potential. So let me give you an example. So with more and more renewables, we expect more periods with lower inertia. So this is when periods that have a lower share of conventional generation. So when this happens, and this has actually happened 3 times in the summer of 2018, the Nordic operators decide to do a redispatching because they cannot afford the loss of very large infeeds. So what happens here is the largest infeed here in the Nordics is the loss of the nuclear power plant Oskarshamn 3. So if we predict a low inertia period, we actually reduce the generation of Oskarshamn 3 and increase the generation in other areas. So this had the cost for these 3 events of 2018 of about 0.4 million euros. So through our investigations, what we see and what we recommend is actually why don't we use the HVDC lines to offer this frequency support? Okay, and the presentation by Matas Diokas right after Andrea will actually focus and discuss in detail how we can achieve that. During faults, actually, why don't we use the HVDC to support frequency? And we go even a step further, and we discuss why not actually use this also during non-critical operation, during the regular operation, right? As we're going to see, the savings that we can achieve is up to 4.88 million euros a year just for the Nordic system. Matas will also discuss about how to control the HVDCs in order to provide this frequency. And so far, this emergency power control that we use has been based on ramp-wise control. So this means that if the frequency drops below a certain threshold, then I just inject so much power without actually monitoring how the frequency develops. So we have suggested, and we have also presented that during the previous event 2 years ago, to move to a droop-based frequency control, where we actually monitor the frequency, and the moment that the frequency recovers, we can stop the sharing. So as a matter of fact, NSOE has published a report this year where it actually proposed the use of HVDC for frequency support, and based on this droop-based control, the results and the studies that have been carried out in this project have actually informed the studies that this NSOE report was based on. And Matas will also talk a bit about this. The question that here comes, if we talk about the droop-based frequency control, is how should we optimally distribute the control effort across the HVDC lines? And this is a question that Danilo Bradovic has been working with over the past 1 or 2 years. So how should we best distribute this? And in the demo later today in the afternoon, we're going to see how we can achieve that. Okay, so this is more about the methods and the insights that we are generating here through this project. But this project is not only about this. We have also worked on creating the models we needed in order to perform these studies. And we have placed them also, all of them online. So you are very welcome to take a look at them and use them for any studies. So the first is a dynamic model of the Northern European system, where we have a detailed representation of Denmark and the Nordics, and the equivalents of the UK and the continental Europe. This is an RMS-based simulation that focuses on the frequency dynamics for large and small disturbances. And you can find that online, and we also have a poster here where we can discuss this more during lunch and the poster session. We also have a detailed model for a static security and power flow of the whole European system, including the UK and the Nordics. We're talking about more than 1,000 conventional generators and quite some renewables. You can also find that online. Based on that, we have also developed a market model, both for a zonal market, that's actually what Europe has, but also a nodal market. And you can also find that online, where we actually use it to assess the market outcomes. So we have also created additional resources. One of them is the multiDC app, as we call it. So you are welcome to go online on this link. So we're going to place all slides online by the end of this event. So all these links will be available. This is an interactive tool. We have uploaded some interesting cases. You are welcome to click on the page and play with it and see how the flows change. We have also produced a white paper about the North Sea Energy Islands. This has recommendations about the topology and operation, what is the impact on the grids and markets, and some of it we're going to discuss today as well. And one more element is the integration of hydrogen and Power-to-X and how this can be done. This is also placed online, and for the ones that are physically here, we have some copies in the back. You are very welcome to take one. So concluding this presentation, let me talk a bit about how we will go forward. So as I mentioned, we're going to have 2 presentations right after this one, where we discuss in more detail the key results that we have generated about specific topics in this project. And then we're going to have the lunch break. And after that, we're going to move to the Power Lab Decay control room here right next to us, where we're going to have 3 live demonstrations about the low inertia North Sea Energy Island, the zero inertia, and and how to support frequency across areas with HVDC. Right after demonstrations, then we're going to have a panel session, and we have the pleasure to have 5 distinguished guests with us. we are going to talk about the energy islands and the HVDC interconnections. What are the next steps towards the integration to the European grid? We have with us Sonia Berlin from KTH, Fitim Krezi from Energinet, Peter Lundberg from Hitachi Energy, Cora Petino-Wagner from TenneT, and Deepak Ramasubramanian from EPRI. Deepak will join actually online since he's based in the US at the moment. The panel session will have been moderated by Jakob Ostergaard. Unfortunately, he has severe back pain and cannot join us today. So I will perform this role. And by that, I would like to conclude this presentation, and I want to wish everyone to a good rest of this event. Yeah. Are there any questions? Yeah. Just for the people online, we just need to make sure that.
It's just a funny question.
Yeah.
I saw you had the Oscars ham on your slide in the summertime. What is doing? I don't think it produces megawatts.
It does actually.
But I think it was actually eating megawatts. This is my.
Well, the events that we have seen actually, it was produced and it had to be produced. Yeah. Any other questions? Great. Thank you very much. Then the next presentation is by Andrea Tosato. Can you? Works.
Okay, thank you, Spiros, for the nice introduction. And thank you, everybody, for joining this event today, and also for the people that are joining online. Thank you very much. So my name is Andrea Tosato, and I'm a former PhD student, now a PhD of working in the multiDC project for the past 3 years and a half. And today I will focus on the work that has been carried out at the multiDC regarding the offshore energy islands. And just a recap, so offshore energy islands, they fall within the category of hybrid projects, that are projects that combine both offshore wind capacity and transmission capacity between the connected countries. And we have seen that Denmark is involved in several projects, one of them already in operation, and new projects that are now in the planning stage. And together with the benefit that comes with these projects, there are also new challenges that we have tried to address with the work that we have done here at the multiDC. So this is the outline of the presentation. I will focus mostly on 3 aspects. The first is the topology and the operation of the offshore energy islands. And I will look at the differences between the zero inertia and the low inertia configurations, and also how to share a power imbalance in the island in case of zero inertia configuration. I will then continue looking at the impact on the onshore grids. So the first part will focus mostly on the offshore system, while the second part will be mostly focusing on the onshore grids, the Nordic system in this case. And then I will conclude with some analysis related to electricity markets. So what is the impact of these energy islands on the connected markets? So to start with the first part, the topology and operation. So we have seen the Spiros presentation that we are considering 2 different topologies, a low inertia and a zero inertia. In this case, we are focusing on the case where the island will be an AC ring, right? So we have an AC hub where the wind farms will be connected to, and then we will have the HVDC links that are connecting the offshore system to the different national grids. And we have the first low inertia configuration where we connect a synchronous condenser to the island, and this is used to set the frequency in the island, the frequency of the offshore system. In the zero inertia configuration, instead, we remove the synchronous condenser, so we don't have any source of inertia in the system, and we look at we use the converters, the HVDC converters, to set the frequency by operating them in grid forming mode. So the main difference here is that before, all the converters are operating in grid following mode. Now we change the operating mode and we use them to set the frequency. So we have looked at two main aspects. So one is voltage stability in the island, and the other one is the frequency stability. So for the voltage stability, we have looked at two different cases. The first one is during normal operation. So from 1 hour to the other, we might have to change the flows over the HVDC links due to market operation or to different wind energy production. And we have looked at what happens when we change the set points of the HVDC links. In this case, we have a 200 megawatt variation. And in the figure here, we can see the voltage response of the system. And in both situations, we see that the system is able to remain stable. Of course, with the low inertia, we have a small variation, but this is negligible. Then we have looked at another case where we actually have a large disturbance, and this is represented here by the loss of a DC link. So the system remained connected to the onshore grids, but we have one link less. Therefore, there is a certain power mismatch. And we can see that still in this situation, the voltage excursion is larger, but in both cases, we can actually maintain system the voltage stability. So in the low inertia, we have less damping, but still we can actually ensure voltage stability. So the second part instead is the frequency stability in the island. And still in the case where we have a larger disturbance, so the loss of a DC link, we have looked at the frequency response in the island. And we can see that with the zero inertia configuration, we almost have no frequency deviation. But so this is represented here with the plot on the left. But if we look at the plot on the right, this is the active power change in the onshore system, and we can actually see that with the with zero inertia, we have an instant variation, meaning that a disturbance in the island will be propagated very fast to the onshore grid. While with the low inertia configuration, we have a larger frequency deviation, but we also have a slower propagance of the disturbance. So if we then focus on the zero inertia configuration and we think how a power imbalance will be dealt with in the island, then in case of frequency droop controllers, we will share the power imbalance among all the converters that are participating in frequency regulation. And here we have a sketch that just represents one operating condition of the island. So we have the import from the wind farms, and then we have all the HVDC links exporting to the onshore grids. And we have looked at the situation where we lose one of these links, in this case, the one connecting to the UK. And what happens is that if we have equal sharing among all the converters, the previous power, the power that was previously flowing on the UK link will be redistributed among the other converters. And what happens if some of the converters were operating already close to their limits is that they would saturate, and eventually they would lose synchronism. And we have verified this through dynamic simulations, and we have seen that actually we have instability in the system. So what we came up with was a different solution that is what we call a master controller, that instead of just distributing equally the disturbance among the different converters, would actually look at what is the headroom, so the available transmission capacity left on each link, and then will distribute the power imbalance according to this headroom. Right. And in this case, what will happen is that the converters that are operating close to their limits have a low participation in frequency regulation, therefore ensuring system stability, because we do not saturate the converters. And how this master controller works, or the principle behind it, is that in order to calculate the droop coefficient for the controller, the HVDC controllers, then we need to have an estimation of the HVDC flow. So we start by looking at what is the possible flow on the HVDC links, and based on this, we use this as an input for an optimization problem, where we actually try to find the set of droop coefficients for the HVDC converters that satisfy N-1 security in the island, so that ensures system stability in case of any imbalance in the system. And we try to also to minimize the distance between these droop coefficients in order to, if there are no constraints, to share the imbalance equally among the converters. And once we solve this optimization problem, we see if we have a feasible solution, meaning that there is a set of droop that satisfies all these constraints, then we give the green light to the market operator, and we give full transmission capacity available. Instead, if there is no set of droop that satisfies this constraint, then we have to reduce the transmission system, the transmission capacity in the system, and then we keep doing this iteratively until the point where we get actually this feasible set of droops. And once we have found this, we then communicate the available transmission capacity for market operation, and the market operator can then clear the energy market. And then we can adjust these droops based on the realization of the flows or closer to real time at any stage following the day at market clearing. And so the main difference of this approach with the fixed and constant and equal droop settings is that we don't have control actually. If we have fixed and equal droops, we know that this is going to be the amount of power that is shared among the converters, and therefore we have less flexibility in terms of defining what is the available transmission to the market. So what happens is that the transmission system operators will have to reduce the available transmission capacity for a large period of time, and we can see that in our simulation this was I mean, we can give full capacity to the market only during 30% of the time, while we have to go below 90% capacity for almost 70% of the time. So if we look at the utilization, then the load factor of the links is roughly 70–75%. But what happens is that if we allow for adaptive droops, so we change the droop coefficient every time the set points of the HVDC is changed, then we allow for much more flexibility in the system. And we can actually increase the load factor by almost 10%. And what does this mean? This means that we will have less wind curtailment, so we will actually be able to import in the onshore grids more wind, and also that we will reduce the cost of generation in the connected markets. So to wrap up this part, so we have seen that there are two configurations that are possible, a low inertia and a zero inertia. We have seen that in both cases we can maintain voltage stability in the system, but we have seen that in terms of frequency, we have much faster dynamics with the zero inertia configuration, meaning that we also transfer the possible disturbances to the onshore grids in a faster way. And then we have seen that if we have only converters in the island, then we will have to use this converter in order to share the power imbalances in the system. And if we are in this situation, that we might want to have a master controller that actually coordinates the converters in order to maximize the transmission capacity for market operation while keeping the system safe. And we have seen that the master controller has been already successfully deployed in the Krieger's flux solution. So we know that this is actually possible. So I will move now to the second part, and we have done similar analysis here, but focusing now on the onshore side. So again, we have the AC hub with the different connections to the different asynchronous areas that are connected to the island, that are the Nordic system, continental Europe, and the UK in our simulations. And what we want to see is, in case we lose one of the links, so we have a disturbance. So how the control settings of the HVDC converters in the island will impact the stability of the onshore system. And in order to do so, we have focused on one converter in particular, the one connected to the Nordic system. And we are looking at the situation where we change the control settings of this specific converter here. So we have started with the situation where we have an infinite droop. So this converter connected to the Nordic system does not participate in frequency regulation. And what we can see on the right plot here, that shows the frequency deviation in the onshore grid, so the Nordic system, we see that there is almost no impact on the Nordic frequency. When we start decreasing the droop coefficient of this converter, we end up with the yellow line, meaning that the smaller is the frequency droop, the larger is the participation of the converter, and therefore the larger is the frequency deviation. But at the same time, so if we look only at the Nordic system, okay, we see that we have larger frequency excursions, but what happens in the other converters that are connected to the island is actually the opposite. So we see that, for instance, this is the one on the left is the frequency deviation in the UK area. And we can see that when we have the maximum frequency deviation in the Nordics, we have actually the lowest in the UK area. So in this part, we have seen that the droop settings, so the control settings of the converters in the offshore system, they highly impact the stability also of the onshore grids. And that this calls for a new regulatory framework to assess what is actually the best way to calculate these droop coefficients in order to fairly distribute the contingencies that are happening in the island among the partner TSOs that are involved in the project. And this will lead us to the last part, that is the impact on the national markets. And as already mentioned by Spiros, in order to perform this analysis, we have developed a large model of the European transmission system. And then we have used this we have derived from this transmission model a market model, where we actually look at the situation of the European electricity market in 2030. So we include all the changes that are foreseen by 2030. And of course, we have focused mainly on the offshore islands in the North Sea, and we have looked at different configurations, different sizes of the islands, and different transmission setups. So we have looked at the first case with one island, 10 gigawatt of wind and 10 gigawatt of transmission capacity. Then we have also looked at a situation with two islands and 20 gigawatt of wind, and then different setups. So for instance, a connection to Norway and more transmission capacity for trades between the countries. And if we look at the results overall, here I'm showing mainly the differences between the 10 giga and 20 gigawatt with the reference case that is the one without the island. And we can see that across all scenarios, we actually have an increase of social welfare, meaning that in all our simulations, these projects are beneficial for the entire system. But what happens is that together with the benefits, we have a number of challenges. So for instance, the plot here shows what is the social welfare variation for each country based on the import-export position, so on the net position of each country. And we can see that the more one country is exporting, actually, so it's a net exporter during the year, then the more negative is the social welfare variation, meaning that the benefits are actually shifting from the producer side to the consumer side, because we see that electricity prices decrease. And therefore, if a country is exporting a lot, meaning that the generation part is like more relevant than the consumption part, then we actually have a loss of revenues for these producers. Exactly. So we have that importing countries benefit more, and exporting countries actually lose part of their revenues. The second thing we have noticed is that there is a call for a higher system flexibility. So the plot here shows the cycling pattern of a thermal generator in DK1. And if we compare the yellow curve that is without the island with the blue curve that shows just 10 gigawatt of wind, then we can see that the cycling increases by 30%. And this is one example, but overall, among all thermal generators in the connected markets, the cycling increases in average by 10%, meaning that we are stressing conventional generators, and this is because of the high volatility of wind generation, of course. So cycling of conventional generator increases, meaning that we need more system flexibility. The third part is the part related to congestion management. And so the plot here shows what is the amount of wind energy production and what is actual the wind curtailment, and that is the orange part. So what we have seen is that once we compare the market outcome and we actually project it to the transmission model that we have, we see that this is not actually feasible, because there are some internal constraints, especially on the German side, that limit the import from the island, meaning that it's very important to select the point of connection for the HVDC links in the best way possible in order to avoid wind curtailment and maximize the actual import from the island. And to conclude this part, so we have seen that there are new challenges, but of course that these projects are very beneficial. If we consider what are the challenges, we see that there is a shift of benefits from the producer side to the consumer side, meaning that we need to come up with a way to fairly allocate the benefits, the cost and the benefits between the participants. But also we have seen that cycling of traditional generators increases, and that there might be internal congestions limiting the import of wind energy on the onshore grids, calling for more system flexibility and grid reinforcement and storage solutions in order to maximize the benefits from these islands. This takes us to the conclusion of this presentation. So we have seen the first part related to topology and the operation of the offshore systems, and we have seen two topologies. One is a low inertia, the other is the zero inertia. We have seen that the zero inertia has smaller frequency deviation on the island, but at the same time propagates the disturbances faster to the onshore grids. And we have seen that in case of zero inertia configuration, we would like to use a master controller in order to maximize the transmission capacity while ensuring system stability. The second part was related to the impact on the onshore grids, and we have seen that the droop settings of the HVDC converters have an actual impact on the stability of the onshore system. Therefore, we need a regulatory framework that says how to select these droop coefficients in order to fairly distribute the contingencies among the partner TSOs involved. The last part was related to electricity markets, and we have seen that overall these islands are very positive for the system, but that there is need for reassessment of the cost-benefit allocation schemes, and also need for increased system flexibility, like power-to-X or storage solutions. So this is it from my part.
Great, thank you, Andrea. Are there questions? Yeah.
Thank you, Andrea, for the presentation. You mentioned that the wind curtailment that was due to limitations in Germany, and I was wondering in your model, do you consider the HVDC connections that are planning to build from north to south Germany?
No.
No.
There are no HVDC, HVDC in Germany.
And from your stomach feeling, would you think that this could help the situation? That
Well,
could
for
reduce-
sure. I mean, we see many bottlenecks, right? In Germany, that there is this problem of transferring power from the north to the south. So increasing the transmission capacity in this sense, especially with HVDC that is highly controllable, would actually help a lot.
Great, thank you.
Great, yeah.
Thank you. Thank you for the presentation. One question you presented in the beginning, and also Spiros presented, you have considered this zero inertia case and this low inertia case. But in both cases, your onshore converters, they are grid following. But I guess you could imagine a third case, and I'm just wondering if you've thought about it. If you have something that is grid forming offshore, it could be a battery, it could be a synchronous condenser, it could maybe even be the wind power. In the future, that would allow your onshore converters to be grid forming. So I know maybe you have not studied this, but do you have a feeling, because you studied this impact on the onshore grid and the opportunity to support the onshore grid, what would be your, you could say, stomach feeling about such a solution? And is it something you've thought about?
Well, actually, the dynamic part, let's say, it's not really my expertise in this. So I can maybe point at Yorgos, might be able to answer.
Let's have a yeah, I think so. To understand the question, it's if we can have both the offshore and onshore operate in a grid forming mode.
If we consider your
only onshore,
low inertia case,
yeah.
Let's say that your synchronous condenser offshore is strong enough. Let's just put it that way.
Okay.
You could actually have your onshore converter in grid forming mode.
Yeah, sure. And having the offshore converter, and having the offshore converter operating in grid following. Yeah, indeed. I would say that the grid following, you have to control the DC voltage of the link, right? The offshore converter, and you have to find a way to relate the DC voltage variation to the frequency variation of the synchronous condenser, right? So you need to have a coupling between the DC voltage variation and the frequency variation on the island to allow for change of the power flow, right? So yeah, but I would assume that it's a feasible solution. It's just a different kind of control modulation.
Yes, but I don't think we should discuss it too much now, but it's just an interesting perspective, I think, and something we're looking into at in Guinness and in the North Sea Wind Power Hub is that maybe for the future energy islands and the full rollout, I think, really loud. For the first step of the energy islands, we believe that, okay, we need the offshore HVDC converters to be grid forming and have this capability. But maybe we think it's an idea level at this time, that maybe the best solution long term, if we really want the large scale rollout, is to have something, if we can achieve it, grid forming offshore. Could be the wind, could be a battery. It could theoretically also be offshore PTX being grid forming. These are just ideas, thoughts. In your case, it could be the synchronous condenser, maybe, which would allow us to have the onshore HVDC converters in grid forming mode and being able to support the onshore grid in a better way, just like you presented, also sharing frequency reserve. So you had this case where you showed the disturbance in the onshore in the zero inertia case, which was quite large when you have no inertia offshore. But if the onshore converter was grid forming and having a sort of inertia response, this could be different.
Yes.
So there was just ideas for sort of future work, and maybe you had already thought about it. But let's just leave it for later. But thank you.
Thank you very much. That's very interesting. Yeah. Let's take a last question. Yeah.
Thank you. I was just curious, you said the master controller, you already introduce the results from this project into Kriegers Flag, or how was it? How was it in the process?
Think we haven't worked on the master controller for Kriegers Flag that was developed by ABB. Yeah.
Okay. Yeah, I was just curious if it was a cooperation or something like this. Okay.
Do you want to add something?
So Rutger was part also of this project and we had interaction with the Okay. Let's move to the next presentation by Matas Diokas.
Yeah. Can you hear me? So welcome to final presentation for the morning session, Smart Management of HVDC in the North European Grid. In this presentation, we will present the main results from the multi-DC work related to the sharing primary frequency results in the Nordic power system. And we'll start with improved HVDC frequency response called using frequency groups. And we show that that it's actually more effective and in terms of technological aspects and economic aspects. We base that on our cost saving analysis, where we calculate the cost of remedial actions during the contingency hours when the Nordic power system experiences low inertia scenarios, and then we present a supplementary power control scheme to exchange frequency reserves over HVDC link during a non-critical operation. And finally, we conclude the presentation with main takeaways. So yeah, let's start with sharing primary frequency reserves. So in power system, the phasing out of synchronous generation and increasing penetration of renewable energy sources decreases kinetic energy stored in the system, which in turn lowers or results in larger frequency deviations when the contingency happens. But at any moment, at any operational moment, frequency response has to satisfy certain frequency constraints, which are designed and set according largest dimensioning incident in the system. In the Nordic power system, this largest dimensioning incident, also called N-1 criterion, is a nuclear power plant, Oskarshamn 3, with a nameplate capacity of 1,450 megawatts. If you lose that event, if you lose that generation unit, the frequency response will experience large deviations, and TSOs, in order to avoid these large frequency deviations, deploy remedial actions such as frequency reserves or yeah, like I mentioned, other remedial actions. And these frequency reserves could come from generators that are already procured on a daily basis in the system. But as well, they can come from fast frequency reserves. This is the new balancing product introduced in the Nordic power system in 2020. But we ask ourselves here, what if we can provide this frequency support from other synchronous areas using HVDC link? And we present here a case about yeah, using that with HVDC control called emergency power control. So to analyze Nordic power system frequency response and these control structures, we developed a simulation model which is based on Energinet and Nordic open source systems, where Denmark and the rest of Scandinavia is modeled in greater detail. And Great Britain, together with continental Europe, is represented with equivalent models. So primarily this tool was developed as a phasor mode simulation tool, focusing on frequency dynamics for small and large disturbances. And also this model includes grid modifications foreseen for 2030 scenarios from 10-year network development plans from respective countries. So you can find out more about the model in a poster session during lunch. In the multi-DC project, we have we have considered two emergency power control schemes. And I will present a comparison between them for loss of Oskarshamn 3, which is the largest generating unit in the Nordic power system, happening at 0 seconds, for kinetic energy of 100 gigawatt seconds. And in these graphs, on the left graph, you will see frequency deviation of the system, and on the right graph, you will see active power injection from the HVDCs in megawatts. So let's start with ramp wise. So this control is currently implemented in the Nordic power system, and it relies on open loop approach, where fixed ramp dependent power injection where fixed ramp dependent power injection takes place at certain frequency levels. And we lose our generating unit at 0 seconds, right? The frequency starts to decrease when it reaches the threshold frequency level for link 1. The link is activated, but up to that point, we have no injection from the HVDCs. So the link 1 starts to inject some power, but the frequency keeps continuing to decrease. So we trigger subsequent thresholds to activate other links. And when we contain the frequency, we already injected 800 megawatts in power system. But as I mentioned, this is an open loop control scheme, so it does not have any feedback to limit the frequency injection once we contain the frequency deviation. So we keep on injecting until we reach 1.4 gigawatts, even though the frequency is contained. So to solve this problem, we propose emergency power control scheme based on frequency groups. And this is a closed loop design where active power injection is proportional to frequency deviation in the system. So if you consider the same case, at 0 seconds, the frequency starts to decrease until it reaches the lowest point frequency nadir. And we can see that active power injection from the HVDCs increases steadily and proportional to that frequency decrease. Once we contain the frequency and improve the frequency response, right? The active power injection from HVDC reduces and participates minimally. So we can contain frequency deviations with Drupa APC using, in this case, 3 times less reserves and improve small signal stability of the system due to the closed loop design. But this Drupa APC comes with certain challenges, and the first challenge is how to calculate these frequency droops among multiple HVDC links in the system. And the second one, what are the most appropriate modeling approaches to perform such frequency analysis? And if you would like to hear more about this, please join a demonstration event in the afternoon. So we have analyzed technical aspects of HVDC droop control scheme. But what about the economic side? Are there any cost savings related to that? And we already know that kinetic energy is decreasing due to increased renewable energy source penetration, right? And here in the graph, we provide Nordic kinetic energy in the system based on historic data for 5 days in July 2018. And you can see that there are ups and downs in kinetic energy, estimated kinetic energy in the system. And at certain points, this kinetic energy breaches the red line, which represents security limit in the system. If kinetic energy drops below that security limit, TSOs might run into a situation that if they lose the largest generating unit, they cannot contain the frequency within the limits. So to avoid that, they take preventive remedial actions. And one preventive remedial action could be reduction of the largest infeed to reduce the impact of the mentioning incident. And this already happened 3 times in 2018, where Oskarshamn 3 largest nuclear power plant had to reduce its output power by a certain amount. And this resulted in a redispatch cost of approximately 0.4 million euros. So naturally, we ask ourselves, can we somehow mitigate the situation using HVDC EPC control? And to answer this question, we designed a decision support tool consisting of these 4 stages. So in the first stage, we estimate kinetic energy of the system, and we perform market simulation scenarios, in this case for 2025. We estimate the status of generators, and together with inertia constants, we can estimate what would be the kinetic energy in the system. Next, we estimate what would be the frequency deviation in the system if we lose the dimensioning incident. And here we can use either dynamic models or historic data. We go further to estimate how much power each mitigation strategy needs to contain the frequency deviation within the limits. And lastly, we estimate the cost of each remedial action. And here we include or rely on statistical estimation of future prices. This could be day-ahead market or reserves market. And we come to a decision. So we consider 3 cases. The first one, down-regulation of dimensioning incident, where largest nuclear power plant, Oskarshamn 3, reduces its power. The second one, fast frequency reserves. We procure additional amount of reserves, and in case contingency happens, we activate additional reserves with FCRD reserves that are already procured in the system. And the third case, frequency support with EPC from HVDC links. In this case, we adjust active power set points to support the frequency during contingency. And here we consider 2 market scenarios. The first one, high load, high wind, considers larger amount of synchronous generators dispatched in the system. And the other one, low load, high wind, considers less synchronous generators dispatched in the system. And we notice that Nordic power system has high correlation of kinetic energy to weather, depending on weather years. So we distinguish, additionally, we distinguish or define 3 inertia scenarios. The one called high inertia refers to wet year, where more hydropower plants can be dispatched. And the low inertia refers to dry year, where less hydro can be dispatched in the system. And from the table, we can see that the most costly measure we can take is actually to down-regulate the largest nuclear power plant, where the cost could be somewhere between 2 and 5.2 million euros per year. We can improve the situation with fast frequency reserves, but yeah, we can improve the situation from with fast frequency reserves with 0.5 to 3.5 million euros per year. But the biggest improvement comes from frequency support with EPC. And in this case, we can save from 1.7 to 4.8 million euros per year. So I will come to the last part, supplementary power control. So up to this point, we have discussed using HVDC emergency control during contingency events where we experience large frequency deviations. But what if we extend this principle to and exchange frequency reserves on a regular basis? So we propose a control mechanism called HVDC supplementary power control, where frequency reserves can be exchanged between asynchronous zones during or on a regular basis, and not only during critical operation. So this is the work this is the problem of unit commitment, where energy and reserves are optimized to minimize the total cost of the system. And this problem includes frequency constraints to comply with N-1 security criteria. So for this study case, we consider two area example, and both areas are approximately twice the size of Denmark. One has the dimensioning incident of 600 megawatts. The other one has 550 megawatts. And these both systems are connected with one bipole HVDC link having 500 megawatt transfer capacity. And we use historic data to define demand, wind, and solar time series corresponding to actual profiles of East and West Denmark from July 2019. So we define here three cases: no SPC, no supplementary power control. In this case, each area uses internal generator reserves. Then unilateral exchange scheme, HVDC EPC is activated only in one direction, and bilateral exchange scheme where HVDC EPC can be activated in both directions. So in the plots, we present reserve procurement in megawatts in area 1, the upper graph, and the lower graph, reserve procurement in megawatts for area 2. And we can see that if we select unilateral exchange scheme, area 1 reserve procurement decreases, while area 2 maintains its procurement amount to support area 1. But if we switch to bilateral exchange scheme, we can see that both areas can benefit, and they reduce the reserve procurement. And they reduce reserve procurement. And this reduction in reserve procurement results in price reduction for reserve procurement, and it could save up from 8 to 11% depending on the scheme that we select. So what are the main takeaways? So from the technical analysis, we can see that Group EPC uses 3 times less reserves and improves system response due to closed loop design compared to RAM5 EPC that is currently implemented in the Nordic. And we can see that by doing so, in certain cases, when the kinetic energy drops below security limit, we can save from 1.7 to 4.8 million euros by adopting this strategy. And then further, we can extend its functionality to include frequency reserve exchange between asynchronous areas during non-critical operation, improving or increasing coordination between different TSOs. And this could save reserve procurement price or reduce the reserve procurement price from 8 to 11%, depending on the strategy we choose. Thank you.
Great. Thank you, Matas. Are there any questions? Very good. Then this actually leads us to lunch that Sid's already getting prepared. And in the afternoon, we'll start at 1:30 with the 3 live demos here in Parallel BK, and afterwards with the panel session. Thank you very much.
All right. Can you hear me?
Welcome to the first demo. Bring your, please. Yeah, the floor is yours.
All right. Good afternoon, everyone. My name is Brynjar Sævarsson, and I'll be giving a demonstration of the low inertia energy island with hardware in the loop. Can you hear me? Okay, then I'll speak up. Okay, so for this demo, we will start with a short introduction to our setup here in the lab, where we will see our simulator and the hardware that we're using for this demonstration. Then we will look into this low inertia energy island and do a live demonstration of its operation. And then we will take a little look at the future and look into what are the critical parameters that we have to be aware of when we want to expand this island. And we will do this by means of a small signal stability analysis and also do a live demonstration. And then we will conclude with a few main takeaways. Okay, so if all of you follow me here into the next room, we will see the setup. Okay, yeah, you can move back, move in. Okay, is that everyone? Okay. So in this big box here is our real-time digital simulator, or RTDS, which we are using here to model this energy island. And we are using these first 2 racks here out of the total of 10. Since we are having this in real time, then we have the unique ability to connect actual hardware to our simulation. And the hardware that we are using is automatic voltage regulator, or AVR, which if you walk with me, you can see back here. Okay. So the RTDS has some input-output cards placed in this little box over here. This gives us an output signal of around 10 volts. That's not quite what we need for the AVR. So we feed it through these measurement transformers, which amplify the signal to the values that we need for this AVR. Now the AVR itself is located in this cabinet over here, which you can take a look into when you walk by it. At the top, you have 2 PLCs, and those are the actual hardware. And then here in the top of this cabinet, we have a computer, which gives us access to the user interface of this AVR. And then if you look over here on the screen, you can see on the screen the user interface for this AVR. And we are currently running a simulation on the RTDS, which is connected to the AVR, and you can see on the screen here that it is the AVR is connected and it's in normal operation. Okay, now we can move back into the control room. Okay, very good. So the system that we are modeling here is a low inertia energy island. So this system consists of an offshore hub placed on an artificial island where we connect 5 large wind farms. And this island is then connected through 2 HVDC links to Denmark and the Netherlands. So the purpose of this island is twofold. First of all, we need to collect all this wind power and distribute it to our onshore grids. And then it also serves as a hub where we can exchange power through the island. And why do we call this a low inertia topology? Well, in this on this island, we have a large amount of converters, around 4 gigawatts in this scenario. But we have placed a synchronous condenser here with a rating of 300 MVA, which is quite small on the scale of the island. And we have also chosen an H value of 2 seconds, which is rather modest. So we're looking at pretty low inertia. So the purpose of having this synchronous condenser on the island is to have an energy storage. So this machine provides kinetic energy. So if we have a disturbance on the island, then the disturbance will propagate slower to the onshore grids. And the synchronous condenser also sets the voltage and frequency references. So we can operate our converters in grid following mode, where they follow the voltage and frequency of the synchronous condenser through phase lock loops or PLLs. In order to control the power of the island, we use the 2 offshore converters of the HVDC links. We do this through simple PI control. Since we have voltage source converters, we can control the active and reactive power individually. So through these PI controls, we can control the active power to a desired set point. And in case of deviations in the frequency, we have also a PI control there to contain and restore the frequency back to nominal. Now we have implemented this in both of the converters, but yeah, in the real system, the integral part would only be active in one of them or move to a separate control, so to avoid them fighting over the frequency. Similarly, we have a PI control to control the reactive power and maintain the voltage at the hub. Now, as you saw in the lab, we have this AVR connected as hardware in the loop. And we have connected this AVR to control the voltage of this synchronous condenser. Now, by having this connected as real hardware, we can test that our model actually works with real equipment. So that's a good validation of its functionality. And this AVR is actually a black box, which we don't have any control over what is actually going on in there. But the overall AVR control is actually split into 2. So we have some part of it in the hardware and some block modeled in the RTDS. Okay, now that I've introduced the system that we are using, we will have a live demonstration. So over here on the big screen, we have some plots, and let's start with this geographical overview where we can see the island, we have the hub, we have the synchronous condenser and 5 wind farms, and then power transmitted to the onshore grids of Denmark and Netherlands. Over here we have a plot of up top, we have the voltage at the terminal of the synchronous condenser, one of the wind farms, and the hub. And down here we have the frequency measured at the same buses. And here we are looking at the active and reactive power of the synchronous condenser, one of the wind farms, and the onshore grid in Denmark. And over here, this is our standard interface to the RTDS, where we have a single line diagram of the system, and we can apply disturbances in real time. So to note, this is not a recording, this is all happening live. Okay, so for our first case, we are simply gonna ramp up the wind power from 600 to 1000 megawatts over 10 seconds and see how that responds. If you press button number 1. So you can see the power of the wind farm, the green one is starting to rise. We are receiving power in Denmark as well. The curve is actually flipped, but yeah, so we are transporting power to Denmark there. And Netherlands is actually exactly the same, since both the HVDC links are identical. Okay, since all these plots are moving, it can be difficult to see exactly what is going on. So if you look back to the slides, we have taken a snapshot of the first few seconds over there. And we can see that the response in the voltage and frequency at the hub is quite smooth. there's not very much deviation, and everything returns quickly to nominal values after we have this ramp. And now, what happens if we have a fault? Now that we've ramped up the power, we're going to see what happens if we have a short circuit at one of the wind farms. And then we will clear that fault after 100 milliseconds, which will result in a loss of 200 megawatts. So if you press button number 2. Yes, there you can see the fault occurring, but the system returns back to normal quite fast after the fault has been cleared. This is good, but yeah, again, it's hard to see what's exactly happening over there. So if you look back at the slides, we've also taken a snapshot here. So what we can see from this is that during the disturbance, the power of the synchronous condenser increases, so it's contributing with power during this disturbance, which means the fault seen from the onshore system is the propagation is slowed down, and we have a more damped disturbance on the onshore grids. We can also note that we have quite a large deviation in the frequency, but as you remember, I said we have chosen a very modest value of H for this synchronous condenser. So this is a very worst case scenario for this system. And another thing to point out that nobody lives on this island, so yeah, it doesn't. So we might not have such strict rules of regulations of how much the frequency can deviate. But with this kind of system, there's always a compromise between how far we are willing to let the frequency deviate and how fast the faults will propagate. Okay, now that we've shown the operation of our current island, what happens if we want to expand this system? We're not satisfied with just keeping it at 4 gigawatts, which we had here, but we want to expand this in the future. So one way to identify some of the critical parameters is to make a small signal model and study the eigenvalues of the system. Now we have this detailed EMT model in RTDS. However, we are not able to just collect the eigenvalues directly from the RTDS. We have also modeled this in Power Factory, but as far as we know, we cannot get the eigenvalues for EMT simulations from Power Factory. And since we have such a converter-dominated system, the line dynamics can also play a role in this. So what we decided to do was build our own state space model in Python, which we then verified by comparison with the RTDS simulations. And this model will be made publicly available shortly. Yeah, and once we verified this model, we could linearize that and check the system eigenvalues. So by doing that, we can see the effect of scaling up the island. So for example, if we look at the effect of increasing the number of wind farms, so without any retuning of any controls, just adding more wind farms, we can see that one pair of eigenvalues is actually getting less and less damped as we increase the number of wind farms, eventually leading to instability. And if we look at the participation factors for this this mode, we can see that the participants are the PLLs of the wind farms and the active power control of the offshore converters. Another thing we looked into was we want to be able to operate this island in the full operating range, so from 0 to full power of 4,000 megawatts here. And we can see that our system is stable in the whole operating range, but there's the same pair of eigenvalues as we saw before actually get less and less damped as we ramp up the power. And we can point out that this has an oscillation frequency of around 8 to 9 hertz, which you will see later. Now, what can we do to counteract this this development? So one thing we can do is increase the size of the synchronous condenser. We can see that if we multiply its rating by adding additional machines, we can actually damp these modes, allowing us to add more and more wind farms. We've also noted that it's not the inertia of the wind farms that is affecting this particular mode. It's the voltage set by the synchronous condenser. Since stiffer voltage set by the synchronous condenser means the PLLs have a stiffer reference to follow. But we might not want to just keep adding synchronous condenser on the island. And we can also see that by tuning of the controllers, converter controllers, we can actually achieve very similar damping. Now, just to note, this is only for a small signal, small disturbances, and the inertia is very important when it comes to larger disturbances in the system. So I'm not saying that we don't need synchronous condensers. Okay, so if we look at the converter tuning, we can see that by increasing the gains of the PLLs of wind farms, meaning we track the voltage faster, or by increasing the frequency droop of the offshore converter, meaning that they react faster to frequency deviations, we can actually achieve very similar damping. However, we have to do this very carefully because when you're tuning some parameter, you're not affecting a single pair of eigenvalues. And we're now just focusing on one, but we have a couple hundred different state variables in the system. So this requires some careful consideration. And we can see that on here that when we're increasing, for example, this green KPF, another pair is actually going the opposite direction. And this has to be done very carefully. Now, to verify that these eigenvalues are actually describing the characteristics of the system correctly, we're going to do a little demonstration where instead of making the frequency droop faster, we're going to make it slower. So by reducing our KPF from 2.5 down to 0.45, we should cross the stability boundary. So if you press button number 3, so now we have changed the value. And what we observe is we're starting to get some growing oscillations, and the system becomes unstable. Now, if we take a closer look at what happened, yeah, we can clearly see these growing oscillations here, meaning, yeah, it's a small signal unstable. And if we zoom in on that, these oscillations have exactly 8 Hertz, which is what we were expecting from the eigenvalue analysis. So what we can conclude is this analysis is giving us useful insights into the critical parameters of the system, and will help us build up the system and expand it in the future. So the main takeaways of this demonstration is we had a low inertia topology, which responds quite smoothly to normal operation where we're just changing the power. We have a synchronous condenser, which gives us a voltage reference for the converters to synchronize with. And we have a slower propagation of disturbances to the onshore system as compared to zero inertia. And for expanding the island, we have shown that small signal analysis is very useful when for identifying the critical parameters. And if we don't design our system carefully, then just expanding it will eventually lead to instability. We've also shown that the size of the synchronous condenser is important. It helps with the stability, both small signal and to large disturbances. But the main thing is appropriate converter tuning. That is the main key for allowing the expansion of this island. Right, thank you.
Great, thanks a lot, Brynjar. So are there any questions? Please, you're welcome to, or comments.
Is it turned on? Yeah, I think it is. Did you try it for the zero inertia case as well without the synchronous condenser?
So we've only done this analysis for the low inertia case. But yeah, the next step would be to explore the zero inertia as well.
Okay, thank you.
We have performed actually, it's way easier actually to tune the grid forming converters in such a case. So we didn't experience any kind of instability. And yeah, we have, to answer your question, we have performed sponsoring stability analysis. To clarify. Thanks. Other questions? Okay, very good. Then we can thank you very much, Miguel, and we can move to the next demo. There has been also a question in the chat from the online. So how have we modeled the VSE converters on the RTDS?
Yes, can you hear me? Yeah. So we have used average models for the voltage source converters, but we have also done it with switching models, but we observed a lot of switching noise, which was giving us issues. So yeah, we decided to move forward with average and perform this small signal stability analysis before moving on with the switch models.
So another question. I thought maybe it's one you can answer together, but I think it could be nice if you elaborate a little bit on the way you see this journey of yours to use the real-time setup for doing simulation. So of course you showed some quite nice results, but we could have done some similar stuff in the offline models in PSCAD or Power Factory. So could you try and describe a little bit for us and for me, was it tough to set up the whole lab? Did you have a lot of practical issues? But also then what are the benefits then you see by going to this real-time world? Yes. Is that we can include some actual hardware in the loop. So we can test, for example, this AVR control and in the future maybe some converter controls. But of course, for general simulations, we could do all the same things with offline simulations. That answers the question.
There you go.
Sorry. Can you hear me? Still, okay. So yeah, the island has two objectives. The one is to collect and dispatch the energy from the wind power parks and transfer it to the interconnected systems. And the other is to allow exchange between multiple AC grids, which can be both synchronous or asynchronous. And again, the configuration that we're investigating consists of multiple point-to-point HVDC links based on voltage source converters. So the main elements of the zero inertia offshore system and why it's important actually to kind of mention what are the operating principles. It's mostly to understand which are the components that contributes to the power balance on the offshore system. So the wind farms, we consider that they operate in a grid following PQ mode. So they provide constant active and reactive power, which means that they don't contribute to frequency and voltage regulation. Then the generated power transfer through AC cables to the offshore converters, who set the voltage and the angle at the corresponding point of common coupling. And their reaction must be fast in order to preserve the stability of the offshore system. And then finally, we have the onshore converters, which has their main responsibilities to control the DC voltage and absorb any kind of active power that it's transferred from the offshore system. And yeah, depending on their location, you can also have either constant reactive power, or you can also have a setting that they control the AC voltage. In our case study, we consider that they provide constant reactive power. And since the focus is on the current limitations, and we want to see how the offshore converters are able to maintain the power balance, we are questioning what is the effect of grid forming converters on the system security. And of course, the positive aspect of it is that they allow for a 100% renewable integration. So they make possible to have a system which consists only of converter-based resources. So we don't have a need for synchronous generation or synchronous condenser, as Brynjar mentioned earlier. And also, we don't have a requirement for having a stiff voltage, which is mostly what the grid following converters are suffering from. However, due to the limited overcurrent capability of semiconductor components, it's very important to distribute the power among the converters in a way to avoid the saturation, especially since we don't have also knowledge of the inner loops that they are used in the grid forming converters. So as Andrea also presented, we have the grid forming converters contributing, being responsible for the power balance. And in case of a contingency, you have equal frequency droop settings, because we consider that all of the converters have the same rating power. The power will be distributed equally among the converters, and depending on what was their operating point at the pre-fault state, some of them can become saturated, and depending the voltage control loop and the inner current control loop that you are having, and the ideal wind-up control loops, controllers that you can have, the converter, you can experience certain kind of instabilities as soon as the converters hit their limit. So what is happening actually is that as soon as the converters that were overloaded at the pre-fault state become saturated, we have a poor system transient performance, and after a while, within few hundred milliseconds, the system becomes unstable. And what we are questioning, or what we are trying to answer, is how we can improve the overcurrent capability. We can have oversizing of the converters, so oversizing of which it might increase the cost, or we can try to control the current under fault conditions. And how we can do that, here I want you to focus mostly on the control structure of a grid forming converter. You have the outer loop, which kind of defines what is going to be the power reference set point and the reactive power reference set point. And we have QV droop and PF droop characteristics. And we have also the inner loop. So we consider two cascaded PI controllers where because we want to have controllability of the current, the voltage endpoint, we want to translate them to current reference set points and then back to voltage reference set points. And we are doing that in the literature in academia. They are doing that in order to be able to control directly the current reference set point. But in order to control the current under the overload incidents. However, and existing work on that aspect, on controlling directly the current references, focusing on prioritizing the active current, prioritizing the active current during the overload incident. However, it has been documented in several papers in the literature that can lead to loss of synchronism, because when the converter becomes saturated, you have a lower maximum power transfer capability. The other also quite common controller that is used, it's a dynamic virtual impedance control, which what it tries to do is to adjust the impedance between the terminal and the terminal of the converter and the point of common coupling. However, if every converter has this kind of virtual impedance controller, there are more parameters to tune, and it has been also documented that that can lead to small signal instability issues. So our approach actually focusing on controlling the power reference set points and controlling the outer loop, since also it's limited the knowledge that we have for a grid forming converter, how its inner loop it's actually designed by the vendor, so it is provided by the vendors to the system operator. So that's why also we are focusing on directly controlling the outer loop by means of adjusting the frequency droop values. And I will try to give an example. So so whenever we are getting, as Andrea demonstrated also in his presentation, whenever we are getting a power reference set point for the converter, we are trying to see if for every contingency that it might happen, all of the converters at the post-fault state operate within the safety region that you can see here, which means that, let's say, if Norway has large available headroom and Denmark has a limited available headroom, which means that it operates quite close to the limits, we will tune the frequency droops so that the power is redirected more towards Norway rather than Denmark. And yeah, the objective of this presentation is to find a feasible set of droop gains during that has to meet certain kind of criteria that is based on the system dynamic performance. And we have to ensure, as I saw, that we avoid the saturation of the converters after the overload incident. So we want all of the converters at the post-fault state to operate within their operational limits that are defined. So we want to tune the frequency droop so that we can make sure that the grid forming converters operate within the safety region at both at the pre-fault and post-fault state. And we are doing that by checking the power reference set points and directing the power to the converters that they have the highest available headroom at the pre-fault state. And I mentioned the dynamic performance of the system. What do we need to consider? Of course, when we update the frequency droops, we are changing also the band. We saw that we are changing the bandwidth of the active power controller. And that can have significant effects to the maximum DC voltage deviations. Also, that might affect the frequency steady state deviations, but also the small signal stability of the system. And I have as a study, I have as a video demonstration. Can I see the file? Oh, thanks. So we will look into the frequency response of the offshore system, the DC voltage response of the HVDC links, and the active power response of the grid forming converters. Oh, now I have to press. So first I will show the frequency. So what I'm doing is that for different frequency droop values, we have a different bandwidth of the active power controller. And for one, we have a slower active power controller, and the other one, when we are increasing the frequency droop, we get a larger bandwidth, so a faster active power controller. Here, the important thing is to see that there are limited, the difference actually between the two responses is negligible, which means also, since there is no inertia in the system, and yeah, pretty much there is no kinetic energy, the responses of the frequency are exactly the same, because we are not having an energy buffer that we can use in order to allow for larger frequency deviations. However, as you will see for the DC voltage, the difference between the two responses is quite significant. So a slower active power controller will allow a larger discharge of the DC link capacitor. And so if you have to compare the frequency, the DC voltage, as a metric, it's better to look at the DC voltage when we are tuning the response of the active power controller. And we want to have a faster active power controller so that we don't allow the DC voltage to deviate that much after the contingency occurs. So yeah, it's what I mentioned, that as a main insight, that faster active power control action is preferable in order to avoid large DC voltage deviations. However, if we make the controller too fast, you can see on the left plot, we are plotting the trajectory of the eigenvalues, and by increasing it at some point, we are entering, the eigenvalues goes towards the right half plane, so the system becomes unstable, as you can see in the middle figure. So there is a trade-off between how fast we can have the active power controller. It's between the trade-off is between how much we want the DC voltage to deviate and how much and what is the small signal stability margin that we need to allow. And why I'm mentioning this thing is that we saw that we want to solve, we want to control the current in order to avoid the saturation of the converter. But by doing that, there are several other aspects that are affected by changing or by trying to change fast the reference set point of the power. So here I will just demonstrate with the adaptive droops. So what we did, as I mentioned, we wanted to ensure that all of the converters will operate at the possible state within their safety region. We saw that we want a fast active power controller, but not too fast in order not to allow the small, in order not to lead the system to small signal instability. And we solved this optimization problem by having, yeah, here I will demonstrate what is the system response with the adaptive droop value. So once we have optimally selected the droop settings. So as you can see, you remember from the first figure, due to the equal frequency droops, all of the converters, they picked up initially the same amount of active power, but here with the different frequency droops, you can see that the Norway link that had the most available headroom picks up most of the active power disturbance. So the system remains stable. Okay. So a summary of it is that with the adaptive frequency droops, we don't really rely, we avoid saturating the converters without relying on adjusting the inner loops and relying on directly controlling the current reference set points. And you can see we improve the transient performance of the system, and we manage to make the system stable. And we do that by optimally selecting the frequency droop values while respecting the DC voltage deviations, the small signal stability of the system, but also the safety region of the converters. So the main takeaways is that, as I saw, the zero inertia configuration, since we don't have kinetic energy, disturbance is propagated instantaneously to the components that contribute to the power balances, in this case, the offshore converters. And due to the limited overcurrent capability of the converters, some of them might saturate after an overload incident. And what we try to do is to control the current under fault conditions in order to avoid oversizing the components. And we do that by adjusting the power reference set point of the converters and not really adjusting the inner loop control. And overall, we improve the transient stability of the system. But since this tool requires the knowledge of the power reference set points, so every time you get a new power reference set point, you have to think of, do I want to adjust my frequency droops or trying to decrease the transmission capacity in order to have more available headroom. We need a predictive tool for the available head to kind of get an estimation of the available headroom, but also a central coordination, because as I saw, it's the North Sea Wind Power Hub is connected to multiple onshore grids, and depending on the size of the onshore grids, some of the TSOs, they might not want to redirect a lot of power to them, so they might want to give a less. They might want to contribute with less active power in case of an overload incident. So thank you.
Great, thank you very much. Are there questions? Yeah.
Thank you for the presentation. So you explained nicely the tuning of the frequency groups, but when you had to reach this small signal stability, did you also, what about the voltage groups? And yeah, did you run into some issues, and how did you cope with that?
Of course, there are several gains that you need. So, but because we choose to update the frequency group values, we keep the, so initially we tune them in order to have a certain small signal stability margin, okay? But because there is a need of updating the frequency group values, we only evaluate later on if I have to increase the frequency group over 0.1, let's say, can I do that, or the system will be small signal unstable? So we are, in this particular case, we only did the trajectory of the eigenvalues is only by changing the frequency group.
Okay.
Did I answer your question?
Yes, but I think something we have seen at least is, okay, you have multiple grid forming converters in parallel with very little impedance in between. And yes, it can be tuned to be small signal stable, but it's very a fine tuning you need. And I was thinking yeah.
There is this, so I saw the problem with the dynamic virtual impedance. So when the current increase more than 1 per unit, you update the impedance between the terminal and the point of common coupling, but you also have the static virtual impedance, or it's kind of active damping controller, which tends to increase a bit the resistance between the terminal of the converter and the point of common coupling. So by doing that, you are kind of increasing the electrical distance between the converters, since they are connected to the same bus. And yeah, we have selected the value moderately based on what is given also to some of the literature. So yeah, an active damping controller is necessary. Otherwise, the system might become small signal unstable.
Okay, thank you. And this system you were showing in the end with the adaptive controls, just like Brynja was showing, was that also this system you show, it was also large signal stable? Did you test that? Like Brynja was doing the fault with the fault.
Yeah, we tested in the You mean short circuit fault? Right?
Yes, if you put a short circuit offshore.
To the cable that is 50 kilometers, and also you have a contribution from the wind farm. So when they get below 0.9, also they can contribute with reactive power, and the system got stable.
Okay.
Of course, yeah, it's for the grid forming converter. It's very difficult to. I haven't seen any requirements of what should be their characteristic during a fault, like what should be the inner loop during a fault. That's why also we here we our focus was mostly on controlling the outer loop and updating the power reference and Q reference set point. But you might make the system stable by having a smart anti-wind up and like a better way of controlling directly the current reference set points.
Okay, thank you. And the last question, the question I've been wanting to ask all day. So now we've seen really nicely the zero inertia case and the low inertia case.
Which one is better?
So which one is the best if based on all the things you've been looking at?
Legal market, I mean, technically.
Let's take it purely technically.
But I have to think of the cost of the grid forming converter.
But let's keep all costs out of the picture.
In terms of small signal stability, I would say the zero inertia case, because of the grid forming converters being able to have you have a larger range of values that you can choose from in order the system to be small signal stable, which is something that I would say it's an advantage of system operators, and you don't have to go to vendors and communicate what should be the value.
Okay.
So I would say it's a bit easier to have grid forming converters. And
so you would prefer...
but I think there is also the protection. It's something that we haven't touched in this topic, and I think since we know how a synchronous condenser behave under fault conditions, from that point and on, based on the point that we stand right now, the low inertia configuration seems more feasible because we know how the components will operate. But that doesn't mean that it's not technically feasible to have the zero inertia configuration working. So I would say the zero inertia configuration.
Okay, thank you.
Thanks.
Great, thank you. Are there any other questions? Yeah.
Okay, for Brynja's case, you showed that you used a inertia constant of 2 for the synchronous condenser. I was just wondering if you used a emulated inertia constant for the grid forming converter.
But you don't have a kinetic energy on the island, so you will tend to discharge the DC link capacitor, so which is not, it shouldn't be the case. So you will need to have a storage on the DC side from which you can extract the energy that you are looking for in order to have an inertial effect. Because right now, like pretty much whatever is generated, since we don't have any inertia constant, it needs to be evacuated. And what we have to make sure is just to avoid the overcurrent limitation of the converter, to avoid saturation of the converters. So you shouldn't think of the grid forming converters as a virtual machine once in this case study, because you don't have an energy that you can extract from so that you have an inertial effect.
Okay.
But why you would choose to do that?
No, I was just wondering if you used an virtual inertia constant for your PI controller in your.
You will see like larger DC voltage deviations, and I don't think that. So you will need a storage on the DC side, I would say. So with this configuration, it's not technically. I mean, it's technically feasible. No, I think it's in terms of control, you can do it, but it doesn't make much sense, I would say.
Thank you. Other questions?
Very strong statement.
Great. Then thank you very much, Heroes, for this presentation.
Thank you.
Just in the meantime, if somebody needs a chair, there are chairs here.
Yeah. Please, yeah.
Have it on for you, so you can close it.
Is it on?
Yeah. Check here if it's mute. I don't think it's mute.
Okay. Okay, yeah. I guess we can start the new presentation or demo. So hello, everyone from my side. My name is Daniel Obradovic. I'm a PhD student at KTH Royal Institute of Technology in Stockholm. Now I'll present some work that we've done here in multiDC related to supporting frequency across areas with HVDC. So here we are dealing with the problems of frequency containment reserves, or FCR, and the HVDC emergency power control, or EPC. These are two known problems, and they have been studied for years with the different points of views. And of course, on one side, we have people in research providing different results. And on the other side, we have TSOs in practice using different methodology for assessing FCR or EPC. But for us here in this work, we focus mainly on two questions. The first one, what is the voltage control impact on frequency response? And some interesting aspects here for us were to investigate different disturbance locations and what would happen if we have power converters working with voltage or reactive power control mode. On the other side, the next question is how we should design our HVDC EPC. We have how that is being done in single mass systems and how we want to use that approach and combine it with some outputs that we got from tackling the question number one, and then use it to properly distribute the gains among HVDC links in order to support our system stability. And then in the end, I will just give some main takeaways. So when we talk about frequency control, of course, we have large power imbalance, and then our frequency deviate. And the most important information for us is maximum instantaneous frequency deviation, or max IFD, that needs to be within a specified margin in order to not to activate a load frequency shadow. For assessment of or estimation of IFD, typically we can use single mass system without inclusion of voltage dynamics. This can be very convenient because we can check the sensitivity to different parameters. We can plan our FCR design for future. We can see how inertia impacts and what is the efficient design of emergency power control. For us, emergency power control is defined as group frequency-based control. And here you can see how it looks in principle. That has been also recognized by respective TSOs, and you can see it in the latest NSU report, where they have also provided the capacities where one synchronous system can support the other, such as you can see that continental Europe could support up to 1,000 megawatts to the Nordic power system, and Great Britain could support Nordics with around 600 megawatts. This is a substantial amount, and we could use it in an efficient way to support the frequency, for example, in the Nordic system. But for us, the question is also how much this slope should it be, or how I call it the gain, and how we should distribute these gains among the HVDC links. So we have single mass system representation of our real big power system, and we know the approach how to calculate IFD, or how to get to that information for FCR and EPC design. Then we're asking ourselves how these values correlate to something that we'll see in reality, in real big or detailed multi-machine power systems, and why there is a specific correlation or connection between them. To answer that, we have to analyze in both of these systems governor and turbo dynamics, which is very important for FCR, of course. That is what is typically being done. But also here we want to take into account voltage dynamics. And on one side, we have load voltage dependency. And on the other side, for us, it's interesting to see the control of power converters, or voltage control of power converters, because in the future, as we are reducing the inertia, we are doing that we are removing the conventional generators and we're installing the power converters. So we have to see what kind of control we are going to specify for those ones. Next, since we need to support additionally our system during low inertia scenarios, we have to realize how we are going to do that, how EPC is going to be distributed. To do that, we need the knowledge obtained from the single mass approach to design EPC. We need the knowledge how voltage control impacts, what's the impacts in the real multi-machine systems. And on top of that, to add the analysis of individual performance of each HVDC link to support the frequency. Here we have a Nordic power system test case that we have developed in multiDC, where we have low inertia scenario of around 104 gigawatt seconds, which is even lower than what the Nordic power system faced recently, around 110 gigawatt seconds. Then we have also integrated on and offshore wind power parks. We have current and future HVDC links, both VSCs and LCCs. Also, we paid close attention to the load modeling, and we have neighboring equivalents, so we can also see how the frequency propagates during disturbances in the neighboring areas and when we provide EPC. For us, the dimensioning incident is 1,450 megawatts in the Sweden 3 area, where we can trip, or it could happen that there is a trip of Oskarshamn 3 nuclear power plant. We cannot violate the maximum instantaneous frequency deviation, which is 0.9 hertz, and we have a typical FCR system strength of around 3,650 megawatts per hertz, which is something typical that you will see in the operation of the Nordic power system. Yes, so FCR and EPC are usually designed for the largest disturbance in the Nordic power system, and that is this first disturbance that you see here in the table. However, there is a value to see how will our system or frequency respond when we have a disturbance in other system locations, even with other amounts of disturbances, in order to realize how this distributed voltage control could impact the frequency response. Also, when we are first assessing the system frequency response, we cannot say a priori what is the worst disturbance. Of course, in single mass system, that will be the outage that has largest active power. However, in real systems, when we use active power, we also use reactive power within specific location, and that could also leave some side effects, and we don't know exactly what will be the worst for frequency, and that's why we want also to investigate other scenarios. And here you can see the locations of disturbances that we have applied. On the top of that, I mentioned some integration of wind farms. And here you can see where we have integrated those ones to reduce inertia and remove the conventional generation. And now the question is for these converter controls that we have from wind farms and also from HVDC VSCs that are in the system, how we are going to control, are we going to put them in the reactive power or voltage control mode? Why is that important? This type of control affects the voltage magnitude of the nearby loads, which is voltage dependent, which active power is voltage dependent. So the changes in voltage after disturbance also affect the active power, meaning that it implies the changes in frequency response. And that's why we think that is interesting. VSC's converters of HVDC are controlled in voltage mode, but wind farms converters going to be checked for both voltage and reactive power control. Here you can see the difference in response for 3 cases. The blue is single mass, and the red and orange are detailed multi-machine systems. When you have these 2 different control modes, voltage and reactive power, and you see that anyhow we are violating the frequency limit, and we will need EPC support. Also, we see here that there is some difference in frequency response, and that could be explained through the change of loads and losses active power after disturbance. And what you can see here with the loads is that after disturbance, the loads decreases because we have that voltage decreased as well. So, and that type of change also supports the frequency or reduces the frequency deviation. On the other side, losses are being increased. So they are negatively affecting, or they're increasing the frequency deviation, just not to that extent as much as loads are supporting the in the other way around. And this is something that we can only see if we include voltage dynamic and analyze multi-machine systems. So here what you saw was the case for the largest power imbalance in the system, but here you can see also maximum instantaneous frequency deviations for rest of the disturbances. And what is interesting to notice here is that, okay, here you can see the limit that should not be violated, but you will always see that a single mass model where we don't include voltage dynamics always gives more conservative maximum IFD. And when we actually have this voltage dynamics that is a bit weaker in the grid, so if we use wind farms with reactive power control, then the frequency nadirs are the lowest. So we need EPC support. And another interesting for me here to see is that, for example, if you have a disturbance in Finland 1 area, then there is a probably largest difference between the case 1 and 3. And the reason for that might be because FCR needs to support, if they are located here, they need to come all the way here to support the disturbance in Finland 1, which will require probably higher losses in the system. Okay, so we said that we need some EPC, and let's see how that will be designed in single mass system. Of course, we don't have too many variables to play with, so we just increase the gain of the EPC until we reach the satisfied frequency margin, and then we verify how much power we are going to use for this service. But the main question is how we then going to use this information to go to real systems and distribute it to our chosen HVDC links. The most important information for us is here available EPC capacity for each link that we need to know. But also, before we do any distribution, we want to make sure that actually the HVDC links are able to support the frequency. So what we did here is that we tested each link separately, how much it can support the frequency nadir or the maximum IFD for these two cases that we have for our multi-machine system, and with the same megawatts support. So in order to have a fair comparison, this is what we did. It is interesting to notice that when we control the voltage for our wind farms, it is always easier for our link to improve the frequency nadir. So basically, when we have the tight voltage control in the system, it's easier for frequency to drop with power disturbances, but it's also easier to bring it up using EPC. Also, we see that among HVDC links, we have very similar performance. The only thing that kind of is only S-Link 1 and 2 are giving 20 to 25% performance that is lower, but that can again be explained for the reasons that in order to support the disturbances of Oskarshamn 3, we need to provide power all the way to the north and again to the south. So that could bring that's the reason why we have reduced performance of S-Link, but other than that, all of them are quite equal. So that means that actually for the Nordic power system case, or the case that we tested, there was no significant change or the impact of the location for the HVDC support. That means basically that the most important factor for us, for the Nordic power system, is how much available EPC capacity we have per each link. And therefore, we propose the following distribution of EPC gain. So to calculate the EPC gain in per units, we take the information from the single mass system, how much total EPC gain we need in megawatts per hertz. We have to know, of course, rated power of each link. And we need to know, and we're gonna then distribute these gains according to the available EPC capacity per each link with respect to the total EPC capacity. And this is the results we get. And this is the response which we get for all three cases. And it is pretty convenient to notice that actually single mass system gives a very similar or almost the same IFD value as we have in other two multi-machine cases. And of course, by using this formula, we avoid that to hit the limits on the specific links and then basically reduce the performance of the EPC. Yeah, so just the main takeaways. Here, what we notice that we have to use detailed multi-machine systems to take a closer look into voltage control impact on frequency response. We saw that loads generally tends to reduce the frequency deviations, losses, of course, depending on the operating point, but usually acts in the opposite way, but to lower extent. And this effect is more pronounced if we are having a weaker voltage control in the system, and especially for FCR cases. All links in the Nordic power system have similar abilities improving maximum IFD. And that's why the distribution of EPC mainly concerns the available EPC capacity. And therefore, we propose the formula for that to avoid any kind of limitations. And we saw that actually also single mass system might, in that case, also might work as well. Yeah. Thank you for your attention.
Great, thanks a lot, Danilo. Are there questions? Yeah.
Danilo, can you go back to page 14? Oh, first of all, thank you for a good presentation. No, one page more. Is that any reason why not all the HVDC connections are included there?
No, there is no. I tested these specific ones.
Okay, so
there is no. I mean, in general, I would assume that not all HVDC links will be available for EPC. Here we have that. If you take a look at this location, we have that they're either quite close or they're of the same type. So I would expect similar performance. Even when I test them individually, just observing the active power response, it's almost the same. So basically here, by testing the HVDC link ability to improve IFD, it can be also referred as testing the location, specific location in the grid capability, not so much HVDC link. It's more about location and the loads around it and voltage control. So that's why I think it was not necessary to show all 19 links. I think this was sufficient.
Thank you.
So I think this is a really nice result, but this is maybe a clarification. But so let's say, okay, we see this is what we need. Let's if we imagine that to implement it in practice, is it correct that I would need as a system operator or the system operators in the Nordic area and so on would have to have the SCADA system or whatever set per balance per hour according to the market, use this formula as you're showing with your model, and then dispatch the group settings, the EPC settings of each HVDC.
Yeah, that's a good observation. And yes, so we would need this in order to avoid the limits, hitting the limits. The wise way would be to track the available capacity, and it doesn't have to be so fast. It can be on an hourly basis or even less. So there are two ways. Either you track and you have aftermarket, you see how much is left and you provide that information and you have a summarized and you have each link, or you determine before the market, you say, okay, we have to reserve this amount for EPC and the rest is for the market to do whatever they want. So, but without having this information, you're getting into risk that at the point that you might need EPC, you are going to violate some limits, so you're not going to get enough power.
Okay.
So,
did you present these results to the Nordic RC, for example?
No, this is the first time I'm presenting this.
Okay, results. It's the first time. Okay. My suggestion would be to try and talk to somebody like the Nordic RC who is trying to coordinate things like this among TSOs.
I would be happy to.
Okay, thank you.
Thank you.
Very good. Thank you very much, Danilo, for this presentation.
Thank you.
So as I said, now we take approximately 15 to 20-minute break, and then at 3 p.m. we'll start with the panel session. There's coffee and cake will also arrive.
Yes, not in that for all the meetings, but the thing is, I got these results like yesterday, day before yesterday. I mean, I'm working on them, but the final ones, the proposals where I went through all the, I didn't show all the case studies because it took too much. No, but I think so there is
Shall we take our seats and Deepa's camera? So I don't think Deepak is seeing us. But yeah, only this. So, yeah.
Oh, I am seeing you all, Spiros. Can you hear me?
Yes. Hi, Deepak.
Yeah. Hey.
Yeah. So whenever you can also turn your camera on the back. And
Yes, absolutely.
That's great. So I will just turn this, or yeah. I guess that you can also see Deepak. And so welcome to this last session of today's event. We had a number of different presentations, and some of the questions that arose, I think they're also very relevant for this session. So today we're going to discuss about the energy islands and the HVDC interconnections, and what are the next steps towards the integration to the European grid. We have 5 panelists with us, and we're very, very happy to have them with us. I think we will all start with a brief introduction and maybe some initial thoughts from each and every one of you before we actually move into the discussion. We have some questions, and we would very much welcome any questions from you, from all of you, both the audience physically here and also the ones that attend this session virtually. So shall I start from the person? Yeah. You can decide how to.
My name is Lumbai, and I'm working for Touch Energy as a global product manager. And I'm very happy to be here. I've been around, born and raised the last 25 years of multi-source. I'm very happy to what I've heard today, because I think it's relevant thoughts, and that's very Okay. Okay. So excuse me then for you that are online. My name is Peter Lumbai. I'm working for Touch Energy as a global product manager. And as I said, everything here has been actually just in line with our thinking, that you are having relevant views on relevant subject. And I think that we are on a tipping point where we actually start to go from just being academic and start doing this in the real life as well. And we will never be perfect. We have been talking, our company has been talking in Sigri about these kind of things since 2010 and so on. That's 11 years we're talking about multi-terminal, but we have never been as close as we are now. And with the climate change, the driving factors from society has never been stronger. So we have a golden opportunity where the stars are quite aligned to start taking the first step. So I'm very happy.
Thank you. Yeah, good afternoon, everybody. My name is Cora Bettina Wagner. I'm working with TenneT TSO in Germany in the energy system planning department, and also focusing on the multi-terminal HVDC plannings. And I totally agree to Peter that the time is ready. I mean, we have this large offshore or renewable integration goals, how we need, which we need to cope with. And HVDC technology, especially HVDC multi-terminal and hub plants are currently one of the options in order to solve this this large amount of offshore integration. And also we are within TenneT, we are really fostering this and trying to make this plans real within the next 10 years, and really happy that we can also rely on industry, but also on a lot of academic partners to solve the remaining issues with us.
Hey, my name is Sonja Berlijn. I'm currently working at the KTH as a professor in the Sustainable Integrated Energy Systems. And before that, I worked at Statnett, which is the Norwegian TSO. As you mentioned, we're going for a carbon neutral energy system by 2050. We're going to be the first continent in the world to be carbon free. And to do that, we need to electrify a lot of things. So we see that, as mentioned today, the need for electricity will rise a factor 4 to 6, so not 4 to 6%, but a factor 4 to 6. That means that we need new generation, and we need new transmission, and we need storage and flexibility. And this new generation, where we're going to do that, it can either be then offshore wind, because it needs to be renewable, and then we need to connect this offshore wind, or it can be like fusion technologies or nuclear technologies or other carbon-free technologies. And currently there are plans for building 400 gigawatt offshore wind, and then you start to understand the challenges that we need to connect this 400 gigawatt to the onshore in the correct way, and then HVDC is one of the solutions for that.
Yes. Hello, everybody. My name is Fizim Kurezi. I work at Energinet, also chairman of this multi-DC event. I've been working with islands since 2018. So I'm very happy to see so many people that are getting involved in these type of projects. When we started back in days, it was called everything from fantasy island to any words you can imagine, but now it's getting more and more concrete. So that has helped me quite a lot to be part of this and trying to give my contribution to push it. And we have heard a lot of good presentation today, a lot of good contribution that has been provided by this multi-DC project. We as Energinet, as mentioned, we are involved in the 2 islands where we are trying to build, and then we have also the consortium, North Sea Wind Power Consortium, together with TenneT Germany and TenneT Holland, where we are trying to take this to a higher level and trying to get these islands to a more international thinking, and trying to find some standards way of introducing or including this enormous magnitude of wind that is coming towards us. So I tend to say to a lot of new people, I'm also new and young, but I tend to say to them, we are living in the best possible time, because we are going through a paradigm shift in the way of producing and consuming energy. So it is nice time to be alive. So
I couldn't agree more.
Yes.
Thank you. Deepak?
Yeah, hey everyone, thanks for inviting me here. My name is Deepak Ram Subramanian. I work with the Electric Power Research Institute here in Tennessee, USA. And a lot of my work is on looking at how can we transform the continental power system here in the US, and of course projects around the world. And EPRI works with member utilities like Energinet. We actually interact a lot with Christian at Energinet for some of these projects, and generally looking at concepts of 100% inverter-based systems. How do you model them? How do you study them? And how do you bring about increased inverter-based resource penetration? So both at the source side and the load side, looking at distributed energy resources and power chronic load. So really interesting to be part of this conversation here, because I think energy islands, the way we are looking at it from EPRI, is not just from an offshore perspective, but even from an onshore perspective, where if you have wide areas of land which is far away from load centers. Like we have places in Texas, we have members in Australia, where you have a lot of land available which is remote from load centers, then having a sort of an energy island in that place could be an effective way to evacuate power and ship it to the load center. So yeah, really interesting to be part of this conversation.
Great. Thank you very much, everybody. Peter and Sonia actually talked about, Sonia talked about this 400 gigawatts of wind that might be expected in the North Sea. And Agita is also preparing itself maybe for the first energy island. I would like to ask maybe, actually Peter and Cora. So first, Peter, do you see also an increase, let's say, in the deployment of HVDC, or what are your expectations about from the manufacturer point of view for the next 10 years, let's say, or 20 years?
I think actually when it comes to the development, first, the last 20 years, when it comes to voltage source, we have increased in power. Today, we're looking into systems that there are planning of 2 gigawatts sizes, and we are looking at voltage level 525. Me personally, I think that that is good enough from a grid resilience point of view. So I don't think that we in most of the part of the world need to be bigger and so on. It's more about to make sure how we could implement this in an industrial way, so we don't have lead times of 10 years per project. How can we get the supply line there so it will take us, let's say, 3 years per systems and so on. So I think it's more about, it's still a car, it will have 4 wheels, it will have these kind of things, but it's the inside. How does it look with the UX experience, the user experience and so on. So we will work quite a lot. How we make it happen together with the customers, the regulators, and how do we actually start getting them to build more than that.
Okay, that's very interesting. Also, the point of view of TenneT, do you also prepare yourselves with HVDC lines, or let's say with grid reinforcements for these developments for offshore wind?
Yeah, for sure. I mean, I agree with now we are in the situation that we have a voltage level of 525, 2 gigawatt, which is which we think it's also okay, because now we can start using synergies, not only thinking from one project to the next project, but having the long-term vision and decide where we want to go in order to, basically define the requirements for the next projects, how we can integrate them faster. And there we also prepare also within TenneT with a kind of standard platform design. For example, we launched the 2 gigawatt program, basically having a standardized platform design for all the vendors, which can host the equipment of all the vendors at the moment. And this kind of functionality or platform design we try to deploy now, of course, in the next projects within the Netherlands, but also Germany, because we are cross-border TSO, and we want to stick to this voltage level in order to be ready using synergies. And as, of course, we see if we want to go this for this further development of offshore islands and multi-terminal offshore plannings, we need to evolve at some point also this 2 gigawatt standard, also maybe incorporating then at some point circuit breaker.
Okay, so this platform is actually going to be in your premises, and then manufacturers will come and test their equipment, or you are going to deploy it?
Oh, actually, it was the hardware, the offshore platform, the big thing, you know. So to have the technology platforms to increase, then I think we have a journey to go, both with a lot of things like brains, like all of you, we haven't talked today so much about we talked about grid form and control. If you ask 25 or 50 people in the industry, what do they believe grid forming is? You will get 50 different answers today. And that is one of the things that we need to formulate the next 25, 10 years or so on. And also, what is the interface? We will have a standard, but I believe if you ask the manufacturers, I think that we will have a standard of certain things, and then inside with the interfaces, it will not be standard. It will be, so we have to find out how this industry's standard looks like.
Yeah, I agree, and that standard is very important for TSOs. because it helps with like simulating, with planning, and also with what does it do in the project management and the project design. So I think the standardization is actually one big element in this.
But I also think standardization there has to be from the perspective of performance and not from control equipment. Just taking upon the point of grid forming, right? There's one thing about you will get 50 different answers for grid forming, but what you would also get is you'll get 50 different ways of implementing grid forming. And each vendor should and will have their own proprietary way of doing it, which means that as a TSO, we shouldn't be unintentionally, we shouldn't pose a barrier to any one way of implementing grid forming technology. So, which means any form of standards that get developed have to be strictly from a performance-based perspective of what the TSO wants from the resource. And as long as the vendor and the plant developer can demonstrate that they can meet those performance requirements, and those performance requirements may change. What may be a good performance requirement or a sufficient performance requirement 5 years from now may not be a sufficient performance requirement 15 years from now, because that's how the grid will change. So being able to have a mechanism where we could also change performance requirements and enable vendors to keep their own proprietary way of implementing such controls and techniques, I think that will have to be the way we have to go forward, and not be over restrictive on what type of control we will implement into these technology.
Yep.
Yes, and
one tiny comment about the standardization. I also very much in line with what has been said here, that the more we standardize, the easier it will become for us as TSOs to deploy, and for you guys to reduce the lead time of the components. But I think we should also be a bit cautious with the standardization, so we don't end up locking you to some technology that cannot be invented upon. So it's just a tiny remark.
No, that's what I mean. That we, if you've been into the industry, the vendors like what we call the functional specification, but we have to find that functional specification at the right level, so it makes sense for all involved parties.
Yes. Yeah, I can say maybe something to this regarding especially the topic of grid forming, which was recently addressed. We also we just published last year basically a guideline within Germany defining this kind of reference behavior. So basically defining for the project some envelopes, for example, for grid forming. Grid forming can be, or the control of the vendors and the response of the asset needs to be in a specific boundary. So we defined an upper and a lower envelope so that we are not restricting the development of the manufacturers, but also defining a behavior which serve our needs.
Yeah, and I think it's also important not to end up in vendor lock-in situations, because they are, it's in the interest, of course, of the manufacturer, but it's not in the interest of the TSOs to end up there. And that's why we need some kind of agreement about how we're going to do that. And we have seen cases where then the controls of two different manufacturers, or maybe even of one manufacturer, who are counteracting with each other. And that kind of situations you don't want to come into. So it is also that we need, for the benefit of the greater good, maybe to open up a little bit more, to not be so worried about the IPR. If you deliver good quote, maybe it's good quality and openness and transparency that will be now more important, because I mean there is the industry is now moving also in a different era. There will be plenty of projects and where the situation was very different for maybe for 15 or 20 years ago, that the projects were not so many and the manufacturers had really to compete. Now we have maybe too few manufacturers, so you are in a different situations, and I hope that allows for a little bit more openness, because we need this openness of what's actually in these black boxes to be able to do the simulations for operation.
We still hope that you compete on the price. That could be a good thing competing on.
Exactly. And delivery time. Yes.
and you might know, maybe Deepak, but on the European scale also, you know that I could just address that we are also part, the vendors has come together in the T&D Europe arena, because we are not sick and tired, we are concerned if we should be in the blame game of not one that want to play ball. So actually we are standing up, yes, we want to find that and we want to be open, but we also like to have, we don't want PhD students to see our full control with all control loops, because then we cannot guarantee our the quality of our. So we will open up, but certain part of that will be black box, because those black box. I have some colleagues who would like to have everything open, you know, within the internally in our company, but we want to lock in also some parts as black box also for people inside our company, because we need to have the quality. So we should find the right level of where we change and where we don't change. So what you have done in your presentation today to play around with the outer controller loop, that might be, you know, the open part of the model, while the inner it will still be, because that is with the quality of the converter and so on.
Yeah, and also the lifetime and
So I would also like to turn to Deepak and ask if this is also a discussion in the US.
Yeah, absolutely. We've been discussing quite a bit about the fact of black box models, about open models, generic models, and how we should really approach this problem from the perspective of what really hits us sometimes is if you don't ask the right question, you won't get the answer you want. Because unless you ask a question, like for a simple example, right? If you ask an inverter vendor, and this is not, I'm not saying this is common or widespread, but it's just based upon experience that we have seen, that sometimes if you ask an inverter vendor, hey, does your inverter trip on overcurrent, for example, right? And they might say, yes, it does. But they may not say that the inverter also trips on phase shift unless you ask them if it trips, right? So this question of how much you ask and how much information you will get leads to the question of black box. Because now if you have an open box model, which you get during an interconnection process, we can always dig into that and see what's happening. But that's also not something which is, it has to be done carefully, because I mean, it comes with the classical dialogue from Spider-Man, right? With great power comes great responsibility. If you have an open box model, we don't want system operators that or system planners, they might be running a planning study, let's say a 5-year out planning study, and they might see some instability coming up, and they have to make a decision on how to mitigate that. And they might say, oh, let me mitigate that by changing the gain in this model to this value, because it can make it stable. But that shouldn't be done if the plant is already commissioned, if you know it is operating in a certain manner. And that's the fear with open box models, because things can easily be changed, but they should not be changed. But it goes to the other side of, if you don't have open box models, then we have to really prepare a questionnaire or prepare a set of guidelines and processes that can be like a checkmark list or something like that, to really tell system planners what all does the equipment do, and not just tell the system planners about, you asked me for XYZ, I'm giving you XYZ, but because you didn't ask about ABC, I'm not under obligation to tell you about ABC. And it's not just a technical aspect here. I mean, I understand that there are other non-technical aspects that come into play here about how much you reveal and whatnot. But I think as an industry, we can work in a way forward that we can start getting a little bit more such information while still protecting that core IP, so that system planners get the information that they want to do the tasks that they need to do, while also vendors are able to protect their core IP.
Good, thank you, Deepak. We received one question from the audience related to standardization, and we have seen that maybe different TSOs actually prepare their own grid codes. But if we go to an offshore grid system, then maybe we need some harmonization. And the question is, if you share this idea, and if you share it, then who should be responsible for coming up with this?
I think at least in Europe, the TSOs are working very close together, both in the let's say in the Nordic countries, as we heard today, but also on the European level. So I think both in European level and on the Nordic level, the TSOs are quite close in cooperation with developing grid codes and stuff like that. So I think there is a lot of harmonization, but we shouldn't forget that the systems are quite different. For instance, there are large differences between the system in Norway and the system in Europe. In Sweden, just regarding grounding, the grounding philosophy in Norway is completely different from the grounding philosophy in Sweden. So it is that you have to find some kind of agreement. But you also have to take in the enormous differences in how the systems are built from in the past, and which philosophies they had when they actually built the infrastructure for about 100 years ago or even longer. And so it's a balance between how much you want to harmonize, how much you want to be open for innovation, and how much you have to adapt for the system that's there. And one of the challenges will be this hybrid AC-DC operation. That I think will be very challenging. And even if you have then some kind of standardization on how the DC grid is, still, as you mentioned, the regulators are very different. So I mean, building a cable or between let's say Norway and the Netherlands was completely different than from Norway to England or from Norway to Germany because of the regulations. And you can only start to imagine if we start to build hubs with 3-4 countries connected to each hub, how complicated that will be.
Very good. Now, I'm following up actually on this question. I'm expanding that because Sonia, you also talked about this hybrid DC-DC. And we see that maybe also for these offshore grids, we're talking about multi-terminal DC. We're also talking about maybe offshore AC grids. And this also relates to the commercialization of the HVDC breaker. So I would like to discuss a bit, what are your expectations with these energy islands and their development? What do you see? How do you see the HVDC breaker getting installed, or having multi-terminal DC or a hybrid AC-DC? I don't know, Fifitim, would you like to?
Yeah, I can try. Yes, if we're gonna have a multi-terminal out there, multi-DC, then a DC breaker is a critical component that has to be there in place. We haven't seen anything that indicates, in order to have a stable system, that you can do it without a DC breaker if you have a full-scale meshed grid out there. That is in terms of the DC breaker. There are, of course, some issues with the DC breaker, the maturity of the components. Very much depends who you ask. We have been in a lot of discussion amongst others, but also with you guys, you Peter, about to get a grab of where are we with the DC breakers. And yes, we're getting closer, but are we there yet? It's a bit difficult to say at the current stage, because it also depends on how you see the DC breaker. Some manufacturers tend to see this as an add-on to the system, while we as a TSO, in order to have a more open market, higher competition amongst it, we try to see this as an AC breaker, like a standalone unit. So matter of which set of eyes you look with, then I think the development there is maybe there and maybe not there.
There's one aspect related to not necessarily only DC breakers, but it can even extend to AC breakers, and not just the breaker itself, but the microprocessor relay that triggers the breaker. Now, where we've been seeing it is that until 5 years back or so on, the relay manufacturers and the protection equipment manufacturers, they also don't in a way reveal what's happening inside their code, right? So they have these microprocessor, they have their proprietary way of doing things. And now there is sort of an impasse, we can say, that sometimes relay manufacturers want to know what an inverter is doing inside so that they can adapt to what the inverter is doing, because the characteristics of the system are changing. But the inverter manufacturers are also a little hesitant to open up to show what they're doing inside, which means that you previously had, let's say, only one entity which had all these black box models because that was their core proprietary stuff. But now you have two entities that have black box models, and we have to find a way to make them all talk to each other and come to a common understanding, because it shouldn't be that only change happens on one side, that only the inverters change completely to satisfy what the microprocessor relays want, nor should it be the other way, that the only relay algorithms change to satisfy what the inverters can do, but in a way come to a common ground where both are talking to each other to really sort out any of the issues that may come up.
From my point of view, I think that that at least from our company, we launched the DC breaker at Sigrid 2014, I believe. But I think that we say that the technology is there, but we don't have a commercial product yet. But in order to make the energy island to start operating, we cannot wait for 3 different vendors of DC breakers. We should prepare for adding them maybe in a later state. But if we wait to get if we wait for the perfect outlay, it will be too late. So we don't let the perfect go away for getting started. So I think that we should maybe prepare to add the meshed grid in the end, but we have to find a way of to start building the energy islands without that as the precautions that we need to have 3 different DC breakers around from the 3 different vendors, because then we will be too late. But from Hitachi Energy, we say that we have in the promotion project, we tested a DC breakers system, 350 kV, 20 kiloamps, and so on. So we are there, but we still don't have a commercial product.
Yes, and I mean, we see all these multi-terminal system solutions are developing. I mean, it needs to be developable in a modular way. So from our point of understanding, I mean, dependent, of course, on the power interconnected on the DC side, but there are solutions and configurations where it's not required to have full selectivity directly from the start everywhere. So we can also, according to the Senelec guideline, we also defined in our working group together, we can also define for the start like partially selective protection zones instead of fully, or maybe even unselective. It depends, as I said, on the DC side interconnected power and on the system topology. But for us, it's really important that the manufacturers, however, agree on specific interfaces so that it will be, or that we are able to also deploy a DC breaker later on into the fields, and which is maybe from another vendor. So this is the most important thing. I think the communication between this later device comes into place with the existing components, and there we are again with the interoperability topic. Yeah.
One tiny comment about the breaker and the expandability. Of course, we can't wait to have a master or time schedule or master plan, because then we will not be able to build anything with the time frame that we are looking upon. But we should still build something that is extendable, that we don't end up in the vendor lock-in or actually not being able to expand it all. So that is the trade-off. And of course, also it very much depends on what are the outer requirements out there, because the Danish island has to be of 10 gigawatt in the future. Could be an ecosystem there that could contain power to X, other X's there, which could be batteries, you name it. Those things also imposes some challenges that maybe you can't do the DC from the beginning at all. Maybe you need a mixer, and that is maybe, without saying too much, maybe that is the direction we see now, that maybe you should start with the AC and then develop on the DC, and then depending on what comes in at the island will define in which area you expand.
Yeah, I think you have a point, because I think it's very important that we start to do something, and then you come into the way TSOs are regulated, because we have said as TSOs earlier that we need to be able to experiment more and on full scale, but then you need permission to do this, and then this is extremely difficult. So if we, it was really a pity that this project that was proposed that was not financed by the European Union, because that would have given the TSOs an exception in the regulations to actually start to do something. So I think this full-scale demonstration project is the way to go, and that is we need to convince then the regulators that we actually need to do something full-scale, even if it's not perfect. But if we build it in such a way that we could replace, you build it, doesn't work, we replace it with something else, I think we could at least take the technology one step further, and I think that would be a big step. And you know, sooner or later you will be in a similar situation, because nothing has an indefinite lifetime. So in 30-40 years maybe you have to replace something, and so no system is static for the remaining part of the life. So why don't we just start with some kind of full-scale demonstration or full-scale pilot? And I think that would be really fantastic if we would get some permission to do that.
Is it feasible to not have the breaker, but have, let's say, define the interface so that we're not in a vendor locking? Is it? Yeah.
I think that is the first step, that we actually are of full steam ahead, at least from the vendor perspective. We are looking into how we should be able to do that. And I don't think that's, as we said earlier today, that is not only then a technical issue, because we also then have to rely on the EU competition laws also. So at least the last 10 years, the people working in the different vendors, we are extremely trained to just keep for ourselves and so on. So we are, this is actually a total mind change for us, that we should start then somehow to cooperate with our industry colleagues and so on. So that we actually also have to have a help from the EU to set up that rules, and that is part of this initiative that we tried actually. So the vendors are actually committed to be part of that journey.
Okay. And the way that this will work at the moment, if we don't have the breakers, that we're going to block the whole multi-terminal grid?
Actually, we had a work since we started to work within Senelec. I don't know when we started it, and you could, it will probably be, if you have a small multi-terminal system, you have a single protection zone, and then you could go step by step. So and I think that that's doable. Yes.
Good. If there are any questions from the audience, just let me know. I will turn to Deepak about the. So, how do you see the future of multi-terminal in the US? Multi-terminal DC. Are there thoughts to install this kind of systems?
Yeah, primarily for offshore, not too much otherwise. And even in offshore, it's just starting to kick off, because the amount of offshore wind projects that we have, only recently the offshore zones have been allocated, primarily in the eastern part of the US. There's a little bit in the western part. But apart from that, multi-terminal, at least from that perspective, is not yet, at least from evacuating offshore, has not yet taken more steam. What has happened, though, is the three interconnections that are there in the US. So the Eastern interconnection, the Western interconnection, and the Texas interconnection, they are all primarily connected to each other through DC. And those DC ties are very old, 15, 20 years, because a lot of them use LCC technology also. So there is thought about overhauling those DC ties and bringing in new DC interconnections to replace those aging ties, and there multi-DC can play a role. So that's the extent to which multi-DC has been happening because of the nature of how the various policies have come into effect.
Very good. Thank you. Are there any questions related to this topic? Yeah. Please.
See, I come around a lot in the world, and I have been in US and in Canada, and there they have a multi device, HVDC device from Quebec to Montreal. And it's a very good place for vendors, I think, because there's a lot of material. So you haven't mentioned it, so I don't know.
It's the multi-terminal, it's on LCC type, the new...
Just a minute, please. The next question is that from the Danish side, we had a problem in this area, because I agree on that we should do something. And we actually got a lot of help from the Swedish. So we are looking at the Sweden. But we had a problem that the guys who made Contiscan in many years ago, they are now dying. So we invested in young ones. There's at least 3 of you here who is backed up by the western part of Denmark. And this is the things we are doing very well. And now we are sitting here too. You were with that meeting we had many years ago where somebody was dying from this institute. So the main thing is about these HVDC connections. We invested a lot of money in that. We was number 2 in the world after Gotland. But in Sweden, they had the guy. So we landed up with the guy, and we also got a lot of help from the Germans because we had voltage problems in Germany.
But I also I appreciate that comment, but there is a lot of HVDC knowledge also in Norway. So there is new knowledge coming up, I think, especially when I work for Statnett, but Statnett is extremely good in this HVDC, and they are requested, their competence and knowledge is requested all over the world. So I think young people are starting to come in, and you know, we are engineers and we write things down, we publish things. And I'm quite sure if we need to working force, we will definitely get the good engineers to do that. And technology is also changing, so it's not necessary so that someone who was good 60 or 70 years ago is good with a modern technology. But you could.
No, but I actually think that we will see quite a, and also the number of projects that will come online.
Yeah.
We'll need a lot of people. So we
Yeah.
need to work both. We need to do less in each project, but we need to have good skilled engineers actually to make things in reality and so on. So yes, there is a good pipeline of opportunities rising in this business.
Exactly.
And right now, what's so nice is that you're part of solving the biggest challenge we have in the world as well.
Yes.
You're part of solving the CO2 kind of problem. That's very good actually now.
Yeah, exactly. And also when you look, for instance, at this new TYNDP, this 10-year network development plan, if you look at the numbers there, what is it, right? 54 billion euro they're going to invest. What was it, every year or something like that? There's enormous figures. And this is very good post-COVID, where a lot of people actually lost their jobs. So I think all this building new transmissions and also then lines and offshore technology, I'm quite sure that it will give a lot of jobs in Europe, which is then both, you know, very good for the environment, but also for this economic recovery. So I think we are in the right business. So
definitely at the right time.
Yeah.
Actually, I have a question to Peter, because you're right, Sonia, that there are a lot of projects oncoming, depending on if they become something or not. But is the industry ready to handle those type of the magnitude of projects?
Of course, we are doing everything we can to build up capacity, but there are of course some concerns, but it's all about HVDC has always been like this. Is this a time when our regulators will stop giving us problems with permits? Is this the time where the economics will be there and so on? Because HVDC has always been struggling with making things happen. You know, the pipeline have always been great. So it's a push-pull actually there. But yes, I think we are ready.
That's great to hear.
Yeah, the pressure is high enough at the moment.
Well, the question is the public ready, right?
No,
because that is what we see. Everyone wants to have clean energy, but no one wants to have wind turbines in the backyard. They don't want to have transmission lines in the backyard. So what can we do to convince the public to give the TSOs faster permission processes? I think that is one of the big questions.
And when TSOs wants to put some more on our tariff, you know, as private persons, we cry out as well.
Yes.
Actually, me personally, I think that we have an educational problem as well.
Yes.
The AC system we have, at least in the Western world, was built between Second World War and 1980.
Yeah.
Since 1980, we have been living on that investment.
Yes.
And now with the exchange of the whole society, it's time to do a new investment, and we should not be shy on saying that it costs to do that reformation. But people think that the energy that supports our internet is just for free, and that's an educational problem we have to tell people that we need to invest here as well.
Yeah, I think that's exactly what I'm always preach, I could say, because I mean, if you look at how much it actually costs in electricity or energy to stream new Netflix movies, it's enormous. So, I mean, I work at a university, so there is a lot of pressure to reduce the carbon footprint of universities, and we have about 6 travels back and forward each year. And then I recently, on the back of the envelope, calculated what our digital footprint was just from doing Zoom meetings and emails, and it came out that that was per person 12 travels back and forward to London. So our digital footprint is really increasing, and no one is talking about it. So I mean, in Norway they are thinking about 50 data centers, 300 megawatts each. I mean, 300 megawatts times 50, it's enormous, and no one is talking about it because everyone is talking about the visual. I mean, I don't say that we should not travel in a more sustainable way, but we should talk about things that, or other things that you don't see, but also consume a lot of electricity. Yeah.
So looking at this demand now that's increasing, and also, I mean, the possibilities to actually address that maybe with renewables. One option is to have HVDC lines. Another option is to have some kind of storage, or maybe they both work in. Yeah.
We need both, because the challenges are. I find it actually that kind of argument a little bit provoking, because as I said, the consumption is rising a factor 4 to 6. So as you said, the current infrastructure we have built between around the Second World War, somewhere there. And we need to double it. So if you have a car that is built for 4 persons and you suddenly start to fit 16 persons in it, you cannot say, okay, let's put a roof box on the car. I mean, it's not going to do the job. So you need to build a bigger car as well. So I think here we need to have, I see all the things that we have, I see a toolbox. Yes, we need flexibility, but that is for, I mean, that's for surviving maybe on the short term, because we cannot build the infrastructure fast enough in comparison to where the demand is rising. So we need all the toolbox. So saying that we not have to invest in infrastructure, no, I mean, if you fit 16 people in a car, you have to invest in a car as well. So yes, we need to build better roads, we need to build better cars, we need more flexibility, of course, but we need everything.
Go on.
Yeah, indeed. Sometimes I have the feeling that there's currently a discussion on cannot SOFWE or maybe we can build less lines if we go for decentralization, or maybe power to X or whatever. Yes, we need it all. We need it all. It's not either or. We need it all, and also decision makers need to have the courage to tell there we are with the education part again. Decision makers need to have the courage to tell that it's not enough just having power to X, just to have storage. It's the entire upgrade of the infrastructure is required.
Yes, indeed.
Actually, I couldn't agree more. I think we should start seeing the other alternatives, the sector coupling as a help. Instead of as a competition, because it is not the easiest thing on earth to get the permission to build the overhead line in Denmark, at least. So if we somehow can get rid of building an overhead line, I think we should go for the other alternatives that can help us in terms of meeting the consumption that this thing is clear for everybody will increase tremendously in the coming years.
Very good. Maybe I can turn also shortly to Deepak and ask, so what is the discussion about, or what is your views on storage and transmission, and actually the power to X future as well, from your perspective?
Yeah, so there is a lot of storage projects being considered right now. But one thing we need to also work towards is storage can come with its own pros and cons, right? In a way, how much storage do you have to build? What kind of events do you have to ride through with storage? Does every inverter-based resource have to come with its own storage? How do you allow them to operate in terms of hybrid plants? So I think definitely storage will be a discussion that we have to actively consider, but I think we also have to work towards complementary aspects like improving energy efficiency, improving the way in which we consume power itself, and look towards the load side to provide a little bit more flexibility when needed, and completely agree with everybody else about the sector coupling, where we are looking at different aspects of heating sector and the electricity sector, transportation sector and the electricity sector. The fact that you're going to have more electric vehicles itself is going to be a big hit on the power system industry because there's going to be that much more of demand from EV. So yeah, so I don't have anything new to add apart from what else was said.
I'm not quite sure if I'm in agreement that was maybe the best thing of sitting in a panel and having some active debate, because I mean, you know that, for instance, I think the storage and demand side response are in some way, I don't know, maybe they are pictured like a pink cloud or something. That would be the solution, because we have seen in many cases, we have seen that it's not the solution. When I worked in Statnett, we did a study, for instance, and we put solar panels on all the rooftops of all of Oslo, and we put batteries and stuff like that. And then we found out actually that it didn't help at all regarding triggering investment, because in the Nordic countries, and you know it as well, is that the highest demand is actually maybe this last 2 weeks of January and the first 2 weeks of February. And unfortunately, there is absolutely very less wind because it's high pressure. So there is not so much wind power, and we need a lot. And then in these 4 weeks, we have to fire up a very environmentally unfriendly power plants, coal power plants, and so on, that actually generate a lot. And the storage, it's nice for it's maybe for a second or two, or a minute or two, a minute or 10, but not for 4 weeks. So then you still come back that you need to build infrastructure. And if you have to build infrastructure, you have to build power lines. I mean, why do you need the batteries then? So, and batteries, are they so good for the environment? So what we see now is that there is a lot of, maybe we should have, where there's offshore wind parks come to shore, maybe we should have hydrogen plants over there to produce the hydrogen. And so when the wind is disappearing, then you activate these hydrogen plants actually to generate electricity. I mean, if we're talking about for flexibility, I mean, small car batteries are not going to do the job. I mean, this is gigantic. And also previous studies in the Nordic countries have seen that actually if almost everyone goes for electrical car, the peak demand only increases with 4 to 6%. Here we're talking about a factor 4 to 6. So the electric cars are on a transmission level, they're not going to be a problem. They're going to be a problem on the distribution level, but there we can find other solutions. But on a transmission level, it's not a problem. The problem on a transmission level is data centers. It is the electrification of the large industry, the steel, the aluminium, the paper industry, etc., the big industries that we're seeing. And then back to you, is that electrification is actually the best way to reduce energy, because energy is everything. So, but just by electrifying, we increase our, make the energy efficiency, I think it was 30%, everything more 30% and more energy efficient. So electrification is a way to make things more efficient.
Very good, thank you, Sonia. So for the remaining time, we have about 7 minutes. I would like to discuss a bit about some of the challenges that you see, and maybe how projects similar to multiDC can actually address those in the future. So, for example, one of the challenges that we have found is the need for simulation tools. So have seen that, for example, we need, first of all, EMT simulations. There's no commercial tool that can actually provide the small scale stability analysis at the moment, at least. And we need more advanced tools of this kind. Yeah. What other challenges do you see? And maybe if each one of you would like to spend a minute to discuss this, that can actually lead us to concluding this panel session. I don't know if there's somebody that would like to start.
I can start from that. Yep. That's fine. So we need improved simulation tools, no doubt about it. But at the same time, I feel we should also be cautious about going into only one direction. That only doing EMT or only doing RMS. I think there's a place for both to sit. What we need more is good, accurate models that are well validated for the particular study that one wants to do. And once we get those good, accurate models, then it really unlocks different kinds of sensitivity studies that we need to do. Now, the question about the stability analysis, the question about, say, things like small signal, things like large signal stability analysis, whether you have to do that in the EMT domain or whether you can continue to do that in the RMS domain, that has to be completely dependent upon the type of study that is being done. If you're looking at an interconnection-wide study, then maybe you don't need to do this in an EMT domain. Maybe you could do it in RMS domain. So I think what's more important, I shouldn't say more important, what is equally important is being able to identify what tool is needed for what study and under what conditions should that tool be used in terms of the size of the system to be studied, in terms of the type of detail of each element that is needed, and then to get a process in order to get these accurate validated models at each time of the interconnection process. So I think that has to go hand in hand with the development of new tools, with the development of faster tools, really make use of the fact that use the right tool for the right kind of study and not try to use one tool for all studies.
Yeah, I think the biggest challenge we have here is not so much the tools, because I think the tools can be solved, like a lot of other technical issues. But what I think we need to start with is talking together. Like the vendors with us and us with the vendors, or vendors amongst each other, and see this challenge as a common challenge and not trying and waiting for someone to come with a golden solution for this. Because if we are just looking at each other, nothing will be solved. So everything starts and finishes knowing that we have an issue here that needs to be solved, and no one of us will be capable or able of solving this alone. So, and those technical things, I think they are solvable. The legal is maybe the issue. No.
I'm really glad
Educational
that really glad that we already started the talking in terms of this preparation for the interoperable. And yeah, of course, in the preparation of interoperable, the model discussion and what we need for it was a big part. But also, it's not finished with this. It's also a matter of methods. Which kind, and so that we can evaluate which kind of tools do we actually need for which studies and which detail level is required. This is in some parts still an open issue. For example, unto which control layer we need to have access in order to have interaction studies on the access side. Yeah, so this is, there's also still some lack of methodology. Which we have to also tackle ASAP, as soon as possible together. And yeah, I think then, yeah, one of the issues, but I think, yeah, the talking has already started, which is good, because the pressure on the high integration goals is very high. And also, yeah, it prepares us directly for the implementation, basically.
I think the talking, of course, there is a lot of talking, and we have a lot of talking on different levels, but I feel sometimes we are trying to reinvent the wheel, and everybody's working on the same thing at the same time, in different forums. And that is what I advocate for, trying to move a bit away from it, because there's no reason of trying to solve something that someone else has solved.
Go a little bit more for open source, maybe solutions or something like
and
that.
we have to accept that some of these processes and methods, and also within a commercial phase, need to be adaptive at some point, because it was also not in the past not that way. The TSOs went to buy one HVDC system, please, and then it was delivered. But this is not working, and this kind of process also needs to be established.
Yeah, actually, I agree with everything that is said. From a vendor perspective, we also need to somehow, in the whole, all stakeholders also work on the regulators, because we have to find the forms to start to, and actually, if we get the pull from the political side, the regulator side, and actually they give the TSOs the incentive to invest, then the vendor will come running and so on. So actually, I think that is the thing that we are missing some parts at the table. We always discuss about all good things we have seen here today. I think these are solvable. When I'm out, even if I disagree, I say the technology will be there when the regulatory framework is there and when the money is there. Because they have spent 100 years to get the financial models to work between these different TSOs. Start working on the hybrid schemes now.
Yeah.
Very good. With that, let me just conclude. So what I came from the discussions, first of all, we need infrastructure. We need to invest in infrastructure. This can be lines, but this can also be storage to a certain extent. We need engineers, and we gradually are getting those. We need standardization and harmonization. And we need, in order to do that, we need to start talking together and also start already building the energy island, even if we're not completely there with everything, develop the interfaces and start having the pilot so that we can quickly move with this energy transition. Thank you very much for your participation and for coming to this event. I have really enjoyed this discussion, and I hope also the rest of the audience. Many thanks. Thank you.
You're welcome.
Thank you.
Thank you.
Now it's actually time for a cocktail reception upstairs, so you are very welcome to join us for a drink.